Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video. All math-based course, and as always, it is an honor and a privilege to be serving you today, as it is every day, here in my virtual classroom. Step on aside as we jump into section 3.2 in the Big Ideas Math Integrated Math 3 textbook on adding, subtracting, and multiplying polynomials. We just came off graphing polynomial functions, and now we're doing things within polynomial expressions. A lot of stuff you should have seen before from IM2 or even IM1, just whatever, from distribution and stuff like that. So honestly, if something really seems familiar to me that I feel like I've delivered this kind of thing to you before in the past or you've heard it, things might go a little bit faster. And there's good reason for me to do that. This problem set has 95 problems in it. You did not mishear me. This problem set has 95 problems in it. Now, they may go quickly. It may be a drill and kill kind of thing, but any little bit, even me writing a bunch, is exhausting in its own right. So I'd love to make sure that I can cover what I can, not over-explain something if I don't need to. Or if we hit a big set of problems, like 10 problems of whatever, the first two make sense, let's whiz through those other 8. Anyway, I'm already talking a lot in this part. Let's go ahead and get started. Jump to the description section down below if you want to download the PDF of this thing or check the timestamps for each individual problem or section, or you want to find the lecture or whatever. We're going to start with the lecture. I don't think any graphs are done here. Let's go ahead and get started on this right now. We are going to add and subtract polynomials, multiply polynomials. I'm going to be honest, I don't think a lot of this stuff is going to look really different from what you've seen before. This should be new here though. Use Pascal's triangle and the binomial theorem to expand binomials. So getting bigger things other than just squaring polynomials or squaring binomials, we're going to cube them, raise them to the 7th power, things like that. That should be new. And that's new as far as core vocabulary goes. Otherwise, like terms and identity, however that's used, are things of old. Adding and subtracting polynomials. Recall, the set of integers is closed under addition and subtraction because every sum or difference results in an integer. To add or subtract polynomials, you add or subtract the coefficients of like terms. Yeah, combine like terms is our way of saying it. Because adding or subtracting polynomials results in a polynomial, the set of polynomials is closed under addition and subtraction. Okay, blah, blah, blah. Wordy, right? Adding vertically and horizontally. Ooh. If they're going to require... Okay, I can do either. I tend to just do horizontal or a lot of mental math. But add in a vertical format, what they're going to do is align like terms. 3x cubed will line up with x cubed so they can add them down. There's nothing wrong with the format. I just don't generally do it. 2x squared will combine with negative x squared. Negative x doesn't have anything to align with, so you get a spacing. And then negative 7 will add up with 8. And here you get the result of that polynomial, this cubic quadrinomial. Now, doing this addition here in a horizontal format, like so, looks like what have you, looks like what they do, and it's a good thing to practice, is they rewrite this kind of in standard form. They put 9y cubed first, 3y squared and negative 5y squared right next to each other, negative 2y and y next to each other, and 1 and negative 4 next to each other. Now notice this had parentheses before, and then after addition, there are no parentheses. Adding this thing doesn't change the signs of these values. Adding a negative is subtraction, adding an addition, adding a positive is addition, adding a negative is subtraction. You combine like terms, you get the result. This is implied, by the way. They haven't mentioned it. Make sure your final result's in standard form. It might start there, but just make sure your final result's in standard form. To subtract one polynomial from the other, add the opposite. So yeah, I would distribute a negative. If this was a minus, distribute the negative. Suddenly that's a plus. That's a minus, that's a plus. You'll see me do a step without parentheses in a scenario like that. So change the sign of the terms and and combine like terms. So that's what they're showing right here. Oh, they're showing examples. So subtracting in a vertical format, I think what they're doing, they're showing subtraction of this quantity, and then they change all the signs. They're saying add the change of signs. This turns negative, this turns negative, this turns positive, this turns negative. Negative, negative, positive, negative. Now combine like terms. Subtraction is being had. There's your result. Again, in standard form. You can do the same thing here. This is exactly what you'll see me do a lot. If they force vertical on me, I'll do it. If they don't, I'm going to do it exactly like what you see here. Okay? You see it with parentheses, then you'll see it without parentheses, but sign change. Combine like terms, you get the result. I'm not saying too much on combining like terms. We should be well aware of it. I'm sure we've been doing it a lot in this whole set. Multiplying polynomials. You multiply each term of the first polynomial by each term in the second polynomial. It's a distribution. Boop, boop. You'll see me do a lot of this. I've never done it in a vertical format. Honestly, I don't know if I feel like I really want to. It's similar to what you would do with like double-digit multiplication or something. This negative 3 multiplies with these 3 terms here. Boom, 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 and you get that. and then the x multiplies with 3 terms here, boom, 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 and you get that. But you got to carry this thing over to this portion, not because it's the tens digit, it's because it's a different degree, because now you need to line up x cubes with each other, things like that. And so you could do it that way. I don't know if I'm really big on showing that unless they force it. They're re-expressing this concept that when you multiply variables of the same base, you add the exponents. So x times x squared is x cubed, things like that. It's quite often missed. You might have an x times x squared and leave it as an x squared. So just be careful on that. This is the way that I wouldn't generally write this step right here, but generally what I would do is just distribute out this way. Y multiplies with 3y cubed minus 2y squared plus 2y, boom. Oh, they actually distributed the other way. Anyway, let's do this. 3y squared plus 15y squared, or 3y cubed plus 15y squared, then negative 2y squared minus 10y, and then plus 2y plus 10. So I would probably do it the other way. I'm just kind of demonstrating what they have, some distribution, combining like terms. So again, I'm going kind of quickly on these things here, not really saying a lot about combining like terms. I'll let them do that. Just make sure you combine like terms and get it in standard form. If you have questions on it, let me know. Like I said, I have 95 problems to do. So multiplying 3 binomials, do 2 at a time. Do 2 at a time. So they're showing you the red right here. Turn the red into what it is. Don't try and over distribute. You'll mess something up. I would mess something up. It doesn't work the way that you think that it does with it. But do one set and then do the next set after that with it. Now multiply these two together. That's the basic thing. Do 2 at a time. Then do the trinomial times the binomial. Something like that. Now, what they did straight from here is FOIL. X squared plus 4x minus 1x is plus 3x minus 4. Boom, boom. Okay, there are special product patterns. Let's get into them. We should know from IM2, the sum and difference one, where you have a plus b times a minus b. The result is what's called a difference of two squares, a squared minus b squared. I don't know why the plus or minus, sorry, I'm looking at, this thing suddenly showed up here. I don't know why it doesn't show up here. I'm guessing that they're going to show these. In general, this is huge for you guys to look at. I want everyone to look at this over here. I'm going to call attention to it. In general, a plus b quantity squared doesn't equal a squared plus b squared. Or a squared minus b squared doesn't equal a squared minus b squared. That's a big no-no. It doesn't equal. Does not equal. Big no-no. It's good that they're reminding you that. And same with cubics. We're going to dive into cubics in a little bit in a second. But also a big no-no of that. They say in general because, it's possible with like 0 and 1 or something like that you can run into that answer. But anyway, where was I getting at? Yes, the difference of two squares does come from a plus b times a minus b. Middle terms cancel out and you get that. For example, here you get x squared minus 9. And here on out, guys, I'm going to go straight into that. I'll say this is a difference of two squares. There it is. Boom. Again, this was taught in IM2. So, and this is probably something you probably practiced a whole bunch, and I want to get it ingrained in you to know those. I don't want to reteach and foil each time. I really don't. Same with these ones, and I've already done them several times in the past from completing the square and all that. A plus b quantity squared, not a squared plus b squared, but a squared plus 2ab plus b squared. There's a whole middle term you can't leave out. Y plus 4 squared is y squared plus double 4 times y is 8y plus 16. And then same thing with subtraction. There's just a minus here instead of a plus. Otherwise, the rest is the same. So 2t minus 5 quantity squared is 4t squared minus 20t plus 25. There you go. Now, these are new. These are the new ones here. Cube of a binomial. And we're going to get deeper into this guy right here. But you'll start to see the pattern of what happens as this grows over time. I'm sure the lecture is going to hit on it. But a plus b quantity cubed. Remember how when it's squared, you had a 2 coefficient here? When it's cubed, you'll have a 3 coefficient there. Now, that's not always, you say, when it's a 4th power, is there a 4 coefficient? There is somewhere, but there are additional terms. So I wouldn't marry to it too much. But as far as one that I guess you could remember is that. Here's the big thing to keep in mind, though. Check out how the a degree lowers from 3 to 2 to 1 to 0. And b goes from 0 to 1 to 2 to 3. So the a degree decreases by 1 each time, and the b degree increases by 1 each time. Now, what's generally going to happen is you're going to have a variable representing one of your numbers. Remember, a is not a variable. A can be a variable like x or z, and b can be like your number. So let's take a look at how this one works as the example for cubing it, because it's not just a cubed plus b cubed, right? So z plus 3 cubed is z cubed times 3 to the 0 power, okay, plus 3 times z goes down a degree, and then that other 3 that's here, that's your b, that goes up a degree, that's 3 to the first power, plus this coefficient 3 times z goes to the first power, the 3 is squared, plus z is gone, now 3 is cubed, like that. 3 times 3 here is 9, that's where you get the 9z squared. 3 times 3 squared here is 3 times 9, which is 27. That's where you get 27z, and 3 cubed is 27. So that's something that we're going to have to get a lot more practice in, I suppose, as we do more of it. We take a look at it. Obviously, we'll have problems with it. I don't even think these are the examples we're going to be doing in and of itself, but these are just examples of special products. And then the minus has alternating signs for minuses right here, a minus 3 here and a minus b cubed there. Just something that's going to take some practice. We could dive more into why that happens and such, but keep in mind, you can always do, like for a plus b quantity cubed, I can turn that into a plus b squared times a plus b. So that'll become, or let me do a plus b times a plus b squared. So that'll become a plus b times a squared plus 2ab plus b squared. So you can expand it out that way and then do the distribution stuff. It takes more time. But you can get there, and that can also prove it. All right, proving a polynomial identity. Oh, they're going to do it right now. Let's prove that a plus b cubed is it. So they start with a plus b cubed is a plus b times a plus b times a plus b. They take 2 of these, make it the perfect square trinomial, and then they do the distribution. They get there. So I didn't know they were going to do that. I haven't looked at the lecture yet. So there's the proof. It gets to that stage. Awesome. You can also calculate 11 cubed doing turning 11 to 10 plus 1, use 10 plus 1 cubed to do that, and then maybe that's faster if you know how to work that stuff out. 10 is like your A, 1 is like your B, so 10 cubed plus 3 times 10 squared times 1 of the first, plus 3 times 10 of the first times 1 squared, plus 1 cubed, and then it gets out to 1331. Some more examples here using special product patterns. So this is using the stuff from before, right? So we do have a difference of 2 squares here, which becomes a squared minus b squared. A plus b times a minus b is a squared minus b squared. You get 16n squared minus 25. This is not a difference of 2 squares. This is your perfect square trinomial. First you square a squared is 81y squared, minus 2ab gives you minus 36y plus b squared is plus 4. And then ab plus 4 quantity cubed, that's an interesting one. AB is like your A, it's like your individual term to start with. So first we cube this guy, then 3 times this squared times the other number to the first, then 3 times this number to the first times that number squared plus that number cubed. They're showing a property here that a times b to the m is a to the m times b to the m, so ab cubed is a cubed times b cubed. We've kind of used that already as well in squaring numbers. And anyway, you get this result. Notice everything's still in standard form. This is the cubes go first and then squareds and stuff like that. Anyway, I'm going fast through these lecture things. They seem pretty basic and things that we've kind of done in the past. Outside of the cubes, it's just the recognition of now you combine like terms or now you distribute. Here's going to be a new part, and maybe I have to spend some time talking about it. It's called Pascal's triangle and how it relates to the binomial theorem. First of all, let me show you where Pascal's triangle is. It's right here. And Pascal's triangle, is infinite. You can generate it forever. It is a pyramid where you increase a digit, a number, I should say. You increase a number each time you go down another row. First row, it's called the 0 row. Row 0 has 1 number. Row 1 has 2 numbers. Row 2 has 3 numbers. Row 5 has 6 numbers, things like that. It's important why they say row 0, by the way. Like, why don't they call it row 1? There's a lot of use of the number 0 in this, and etc., and so on and so forth. Anyway, if you see the pattern here, first of all, the 1s go down the sides. I think that's just an important thing to make sense of. And then any number that's the child of any 2 numbers above it is the sum of those 2 numbers. 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 1 is 3. 1 plus 3 is 4, etc. 3 plus 3 is 6. So you can see this generated. Meaning if I wanted to make another row on this, what would I do? I'd put a 1 here. I'd do 1 plus 5 to get 6. This is 15 and 20, and their symmetry, 15, 6, and 1. That would be the next row in this thing. Now, why does Pascal's triangle exist? I'll tell you what, there are a lot of things that Pascal's triangle has embedded inside of it, and I'm sure that this section, it has 95 problems. I'm sure this section's going to talk about it. One of the things among them helps you come up with binomial expansion, use of the binomial theorem. If you have any binomial raised to a power for a whole number n, you can use Pascal's triangle to have as the coefficients in your binomial expansion of that number. And they're showing you that right here. When you have a plus b to the 0 power, well, that's just 1 straight up. That coefficient 1 is in existence with that. A plus b to the first power, you guys know, is just a plus b. But a plus b doesn't just, it also means 1a plus 1b. These two numbers represent the coefficients of the ones that you see right there. Remember your a plus b squared, a squared plus 2ab plus b squared? That's 1, 2, and 1. Those numbers are right there. And so on and so forth. Remember what we just talked about with the cubes? A plus b cubed is 1, 3, 3, 1. Those are the numbers that appear right there. And remember how I said to the fourth power the 4's exist? 4's exist there. They're right here, but there's a middle number 6. Where does it come from? 3 plus 3 in Pascal's triangle. So if you, and you can build Pascal's triangle on your own. Look, you can do it whip fast. You can do it just on the side for whatever. It can be given to you. But using Pascal's triangle, these are the coefficients, the initial coefficients that go in front of these numbers before you have to multiply them out in your examples. Now, they're going to do examples with us. We're going to do some in the problem set as well. But these are the numbers that go into frame as you keep expanding this. By the way, we only went out to the cube as far as how the powers go. Remember how I said a goes down 3, 2, 1, 0? It keeps continuing. Let's look at the fifth power example. Look at a to the fifth, then the fourth, then the third, then the second, then the first, and then it's a to the 0. B increases. It starts to the 0 power. Then it goes to the first, then to the second, then to the third, then the fourth, then the fifth. If there's any recognition you can have with these things here is each degree is 5. 5 plus 0 is 5. 4 plus 1 is 5. 3 plus 2 is 5. 2 plus 3 is 5. 1 plus 4 is 5. 0 plus 5 is 5. They should all have degree 5 in the end, no matter which, well, not truly because B might not be a variable. But, you know, all depending, my ice maker's running. No matter, so it might not truly be, but when you write it out, those exponents should always add to 5. I think that would be helpful. And same with 4. These should always add to 4. 4, 3 plus 1, 2 plus 2, 1 plus 3, and 4. Let's see what they have to say outside of it. I might have already mentioned it all. In general, the nth row in Pascal's triangle gives the coefficients. Yep, that's what I said. Here are some other observations. An expansion has n plus 1 terms. Yep, so the fifth row or due to the fifth power, you'll have 6 terms. I kind of mentioned here it has 6 numbers. The power of a begins with n. Okay, I was just mentioning this. The a's decrease the exponents by 1. The b's increase exponents by 1, starting from 0. And the sum of the powers of each term is n. So I just mentioned all that at the end. I probably should read ahead, but I don't know what the book's going to say. And I don't want to forget. So, all right, let's see some examples. Let's expand x minus 2 to the 5th power, and let's expand 3y plus 1 to the 3rd power. Now, these are all written for us, so let's go ahead and use what they have. X minus 2 to the 5th power. Now, treat the negative 2 as b, unless you know to alternate signs later. But treat b as negative 2. And it looks like they're going to do the same thing. Negative 2 is here. So we'll always have pluses in between, so you don't actually forget what to put there. These will always be pluses. Negative 2's are always there. Now, what we really practiced in the last section that we had was knowing that negatives raised to an even power are positive. Negatives raised to an odd power are negative. Keep that in mind. Now, x is going to be raised to the 5th power, then 4th, 3rd, 2nd, 1st, and 0 power. Negative 2 is raised to the 0 power. You can't see it. Then the 1st power, 2nd power, 3rd, 4th, and 5th. What are the numbers in front? These are the coefficients in row 5 of Pascal's triangle. 1, 5, 10, 10, 5, 1. You can see right here. I might have to draw it for us and have it just on the spot and ready, or they might have it provided for us, but those are the coefficients. And now you got to start doing work, right? You're not done. You have to do 5 times negative 2 to get negative 10. 10 times negative 2 squared is 40. 10 times negative 2 cubed is negative 80. 5 times negative 2 to the 4th, 5 times 16 is positive 80. And then negative 2 to the 5th is negative 32. All of these with the x's involved, all of them in standard form. That's your final answer. That's a lot faster. A lot faster than doing. By the way, x minus 2 to the 5th power is not x to the 5th minus 2 to the 5th, right? It's a lot faster than doing 5x minus 2's, doing foiling, and like I said, do one at a time. Even if you knew that perfect square trinomials led you to x squared, you know, this, you did 2 of these, or even if you knew your cubic one, that x squared, well, actually, that would take some time. So I would probably do 2 of these here, and then the x minus 2. And then you distribute the trinomial and then a binomial. That takes much longer. And that's a small set of numbers. Now let's go to this one. Let's look at, it's only cubed, but 3y plus 1 quantity cubed. If you didn't know that cubic expansion one, use the Pascal's triangle thing, which is probably what I'm going to, well, we'll see. We'll see. But this one here, it's still the idea. You got 1, 3, 3, 1 from Pascal's triangle. I guess this is that thing. 3y cubed is 27, 3y quantity cubed is 27y cubed. 3y squared is 9y squared times 1. These ones aren't really getting in the way, right? 1 squared is 1, 1 cubed is 1. They're kind of, you can kind of ignore them. Kind of just get rid of those ones and just deal with this. 3 times 3y and 1. And I think you'll see that time and again if I have to deal with those in the same way. All right, the coefficients in the expansion of a plus b to the n can also be represented using combinations. So we did combinations in chapter 5 of IM2. 0 choose 0. If you don't remember how these things work, you do have calculator options to bring this stuff up. But for example, 0 choose 0 is, excuse me, I don't want to use 0 choose 0. Let's use a different number. Let's, I guess 3 choose 1. 3 choose, or sorry, n. N choose r equals n factorial over r factorial times n minus r factorial. If you don't remember that, I guess that's okay. You can use the calculator for it. The idea is Pascal's triangle has a lot of things built in it, and some of them are the combinations of those values. And remember how I said zeroth row matters? It's not just what power you raise it to, it's also the elements that you choose things out of. This is 0 choose your numbers. Row 1 has 1 choose your numbers, 2 choose your numbers, 3 choose your numbers, etc. And those generate those coefficients. It's okay if you don't know too much about that for now, but 3 choose 0 is 1, 3 choose 2 is 3, things like that. Plenty of symmetry on that stuff. I'm not going to talk about combinations. That's not the goal of them. It's just saying that's another relationship in Pascal's triangle among your things. There are other things. There are a lot of them. A lot of them are cool. A lot of them I don't know or remember. Some of them have magic numbers. Some of them talk about the powers of 11. Some of them talk about Fibonacci sequence. There are lots and lots and lots of things that Pascal's triangle has. I don't know if some of them were happy accidents or if all of them were by intent, but there it is. The binomial theorem. We already talked about it. That looks more confusing to you than you'd think you'd know. But each term in the expansion has the form n choose r times a to the n minus r times b to the r power. Let's nip that in the bud for now unless it absolutely has to be used. They're using these examples here using 3 choose 0 instead of calling it 1 3 3 1, right? They're using the combination versions. That's not necessary to us. The only time I might look to use it is if they're asking for a specific number. Let's see if they're asking us to do that here. Oh, here's that formula, by the way. Use the binomial theorem to write the expansion. Find the coefficient of x to the fourth in the expansion. So here's the one where you might want to use it. When they say the coefficient of x to the fourth, they're referring to the specific term that has 4 in it for x. Now the one that'll have 4 in it for x is when this, we're looking at this example here. Remember how these things work as far as like the 3x would be raised to the 4th power and the 2 would be raised to the 6th power at that time. Now we need to find the coefficient that goes with that. 10 is a very massive number as far as I don't want to expand Pascal's triangle to 10 rows, so I'd rather come up with the combination that I'm supposed to use in that. Keep in mind when you do this, look how Pascal's triangle builds. You start with your element choose 0 and then choose 1, choose 2, etc. So when we have, remember the 6 aligns with whatever we're choosing here. So when we do 3 choose 2, this b is to the 2nd power. So when this is to the 6th power here, we're going to look for 10 choose 6. So we can either use our calculator for 10 choose 6, or we can actually do this formula thing. I'd rather use the calculator at that point. Where do they have that here? They have it right here. 10 choose 6 times 3x to the 4th times 2 to the 6th power, and then you got to compute this stuff. It becomes a big number, but we're not expanding everything. We're just finding that one specific term. I'd understand if you didn't fully understand I understand if you didn't understand, but I'm sure they're going to ask us more than one question with that, but that's the single coefficient that goes there. I want to generate one with you guys instead of having it pre-built. I feel like it's a lot to state. So listen, if they force binomial theorem on us to do it, I I don't know. I'm not going to use combinations unless I absolutely have to. Or unless Pascal's triangle is something so big. If it's to the 8th power, like I said, to the 10th power, I'm not going to build Pascal's triangle up that many rows. So I will be fine using combinations in those scenarios, actually, when it comes down to it. These are also good for statistics questions. I wonder if there will be statistics questions thrown in the mix. All right, we're done with the lecture portion, about 25 minutes in. Let's go to numbers 1 and 2 on the vocabulary and core concept check, and then we have 93 more problems to do after that. Number 1 on writing, describe 3 different methods to expand x plus 3 quantity cubed. Well, I'll just show you. There's x plus 3 times x plus 3 times x plus 3, which I'm not going to actually do that. Or there's x cubed plus 3 x squared times 3 plus 3 times x times 3 squared plus, let me put these in parentheses so you know what I'm actually doing, plus 1 times 3 cubed, like that. Or there's using, I guess, the binomial one that we were just talking about. There's 3 choose 0 times x cubed times 3 to the 0 plus 3 choose 1 times x to the 2nd power times 3 to the 1st power plus 3 choose 2 times x to the 1st power times 3 squared plus 3 choose 3 times x to the 0 power times 3 cubed. And this last one that I chose, or that I showed you, is a less simplified version of the one up above. Like, this turns better into that when you get some things worked out a little bit more, if that makes sense. So there's that one, and then there's this one and that one. Those are 3 different ways we can expand it. All right, is a plus b times a minus b equals a squared minus b squared an identity? Explain your reasoning. Truth be told, I don't know what it means to be an identity. To me, an identity means something that's going to equal 1 or something like that. Let me think about what they're asking with that. I think they're saying an identity of... I think they're saying that it always holds true. So, yes. So I'll say yes. Because when yes, because it always works. When you multiply the sum and difference of 2 numbers, it equals the difference of their squares. It equals the difference of their 2 squares. I think it just means, like, does it always apply? So I'm going to say yes. All right, guys. So I was going to say, that ought to do it for this one. No, that ought to do it for the vocabulary and core concept check. We are now going to jump into, probably taking a sip of water in a second, but we're going to jump into numbers 3 through 95. I don't even have my thing up. There it is. All right. Okay, guys. Find the sum, find the difference. They do not require me to use vertical or horizontal. I'm going to use horizontal. That's the way I go about it. So, number 3. I have 3x squared plus 4x minus 1 plus negative 2x squared minus 3x plus 2. And I'm sure I could skim this to take a look, but so far that's standard form plus standard form, which is nice. What I'm generally going to do, and there's probably no change for me ever from doing this, but I'm going to rewrite this now without parentheses. Adding negatives means these become subtraction, and then adding a positive means it remains addition. So now I just combine like terms. This is the only time I'm probably going to do this unless I feel like it's necessary for other problems. I'm going to rewrite these so they're next to each other. 3x squared minus 2x squared plus 4x minus 3x minus 1 plus 2. Just reminding you of how you do it when you rearrange them. My plan is not to do that really ever. Oh, look at that answer. And that's what it simplifies to, x squared plus x plus 1. So anyway, I just wanted to show that step right there. You're probably not going to see me show that step quite often or anymore. Unless, again, I feel like it's necessary or it feels right to do so, but not there. But to show one more time, like terms, you want to arrange next to each other. So boom, 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 and boom, boom. And I kept it in standard form meanwhile. Okay, number 4. We have negative 5x squared plus 4x minus 2 plus negative 8x squared plus 2x plus 1. Yeah, you know, when it comes to these questions as well, as I have time to now write this without parentheses, it's very possible that this video doesn't end up being as long as I fear that it could, because these can go pretty fast, right? So these two, negative 5x squared minus 8x squared is negative 13x squared, 4x plus 2x is 6x, negative 2 plus 1 is negative 1. So I think that problem might have taken less than a minute. The thing that takes longest almost is just copying down the original problem. All right. So number 5, especially when the problem gets a little bit bigger over time. So look at number 5. So 12x to the 5th minus 3x to the 4th plus 2x minus 5 plus 8x to the 4th. I should be writing smaller than I am. Just in general, not just to fit it. I feel like my handwriting has... What's the opposite of has regressed? I don't know. Next problem, I'm going to try and pay more attention to it. I'm like focused on writing speed. But anyway, what you see once again for these sums, they say find the sum. Each of these, I'm just rewriting the original problem, but without parentheses, basically. Anyway, there was no other fifth degree term. Negative 3x to the 4th plus 8x to the 4th is 5x to the 4th. I have an x cubed term right here, though, part of the standard form over there, so I'm going to use that one. I don't see any squared terms. 2x plus 4x is 6x, and negative 5 plus 1 is negative 4. So probably more than a minute. What I could do is not rewrite the original problem. If you're fine with me doing this for the next 3 questions at least, not write the original problem with parentheses and just rewrite it without parentheses. So let's rewrite without parentheses 8x to the 4th plus 2x squared minus 1. Now when I add these, treat the signs as they were. This is positive, add it. This is negative, subtract it. This is positive, add it. This is positive, add it. That'll save me some time as well. So now I get 8x to the 4th. I got a 3x cubed right here. 2x squared minus 5x squared is negative 3x squared. I got an x term here. And then negative 1 and positive 1. You know, which is 0. Those cancel out. You know, adding vertical can save you from missing steps right there. One thing that you might want to do as well, I just wrote as those canceled out. Actually, let me show you this. One thing you can also do is when you write something down, like I wrote 8x to the 4th, cancel it out. And then get to your cubes. I've looked for all my cubes. That's the only one. Cancel it out. Right? I go to my squares, find them, write it down, cancel it out. Or, you know what I mean? I should have canceled that. Write down the 7x, cancel it out, and then the 1s cancel out naturally. So, I don't know, right? That's something you can also do. Just giving you little tips. Just don't make a mistake, right? Just combine like terms. Now, number 7 has even more terms. Again, I'll rewrite it without parentheses here. So I got 7x to the 6th, because the problem's already written on that side. 7x to the 6th, 2x to the 5th. I like that they start off in standard form with these things, and maybe that's why they like to do rewrites of these things and put them next to each other. But I always do hunt and seek and look for those things. I'll probably do the canceling out thing this time to show you and see if you like it. So first I'm going to look for largest degree. That's 7x to the 6th. So I'll get rid of that guy. Now let's find 5th degree terms. 2x to the 5th, 5x to the 5th. Add those together, you get 7x to the 5th. So now it's not only that you know you've taken care of them, it's that you don't have to look at them anymore. You know, I'm going to look for 4th powers. I can skip those. I can skip that. Nothing in the 4th power. 3rd power, I have just this one, 8x cubed. Right? Unless I wrote something wrong. So 8x cubed. Now the x squareds, negative 3x squared minus 6x squared. And then 9x plus 2x is 11x. And then there's a minus 5. So minus 5 is right there. I can absolutely see that as a happy medium for individuals who are not trying to write too many things, but are absolutely just trying to make sure that they've accounted for every little thing that they had. So if you like that one, go for it. I will not do that for number 8. Number 8, I'm just going to go straight into it. Still standard form. Plus the positive, plus the negative, plus the negative, plus the negative. Okay, x to the 4ths look to be first. 9 and 11 add to 20. Notice, by the way, the exponents aren't adding. 4 plus 4 isn't giving you 8. These are just alike right there. But when we multiply them, they do add. Anyway, cubes. Negative 3x cubed is the only one. X squareds, 4x squared minus 4x squared are gone. This is the way I'll show canceling on that. Those are gone. 5x minus 11x is here. 7 minus 9, negative 2. Okay. Okay, that's the addition of those. That was 6 problems. That one I think okay is terms of speed. 9 to 14, let's find the difference. I'll keep this list like that just so you have the sums on top. I'm going to go back to writing the first 3 sets with the original parentheses, the original problems. After that, I'm going to just, not. So I start with 3x cubed minus 2x squared plus 4x minus 8, and then minus the next quantity. So the difference on these ones, and I've stated it before, and I'll show you the visual of this here, is we're now going to distribute the negative. We're not doing a whole multiplication like this, right? It's not a multiplication of all that. It's just there's a negative that distributes into these, which means we change whatever signs were there. And it's only the one that's following it, not the initial. The initial, you just rewrite without parentheses. No biggie. But now you change these signs. Subtract the positive is minus 5x cubed. Subtract the positive is minus 12x squared. Subtract the negative is plus 3x. Subtract the negative is plus 4. Now this will look just like the addition problems we did. There's literally virtually no difference on this part than this part, other than they're 2 different problems, right? But now that it's written without parentheses, yes, these signs change, but now that they changed, everything's the same, right? 3x cubed minus 5x cubed is here. Negative 2x squared minus 12x squared is here. 4x plus 3x is here. And negative 8 plus 4 is here. And that's the result. That's after subtraction. Addition obviously has a different answer, but once you arrive at the stage when there are no more parentheses had, provided that you did the correct distribution of the negative, it's no difference than the sum kinds of questions as far as strategy goes. But that's why I like rewriting it without parentheses, period. Getting into that place of the problem where you feel most comfortable. Now, when we do this vertically, I think a lot of things can be had where people make mistakes. In fact, I think the next section is on dividing polynomials. There's a little bit where I do, we subtract vertically on those ones, but I don't change signs. I'm just to forewarn you on that. Anyway, we get to distribute the negative again this time. So distributing negative here. Once more. This last time I'll show the arrows, but 7x to the fourth minus 9x cubed. All right. Subtracting the positive and the positive and the negative and the positive and the negative. The signs change. The signs change from what they were. Now we treat them as they are. X to the fourths go first. We got 5x to the fourth from 7 minus 2. Negative 9 minus 3 is negative 12 for the x cubes. That's a 1x squared, so negative 4x squared plus 1x squared is negative 3x squared. 5x minus 1x is 4x, and 6 plus 4 is 10. Other little things I'll see people do when they're getting so deep into these things. 5x minus x is negative 4x. I don't know, somehow something turns negative. That's unfortunate. Don't really want anything like that to happen. Number 11 is the last one I'll do where I'm writing the initial parentheses set. After that, I'm going to just rewrite it as if the problem was just on that side. 5x to the 6th minus 2x to the 4th. They've all been in standard form so far. Let's keep them that way. Okay, but this time when I distribute, plus 2x minus 11. This time when I distribute, I'm not going to show the arrows. So it's really just a sign change of those, right? You know it's a minus. So you know it's a minus. So change this. Negative, positive, negative, positive. Negative, positive, negative, positive. Right? All right, x to the 6th power, none others exist. 5x to the 6th is the leading term. I got an x to the 5th right here with none others, so negative 7x to the 5th. You got to remember, within this polynomial itself, there's nothing that will combine. Within this, there's nothing to combine. So you're saying, I got an x to the 5th to here. Do I have one here? Yes or no? There's only one. 4th power, I have one here. Do I have one here? Yes. So negative 2 plus 8 is 6. 9x cubed, nothing there. Any x squareds? No. X's? Yes, and they cancel out. 2x minus 2x is 0, not x. It's 0x, which is 0. Negative 4 plus 11 is 7. A 5-term, 6-degree polynomial. And that's number 11. Let's move on to 12, 13, and 14. These ones, again, the problem is written there. I'm going to rewrite it right now. No parentheses, negative already distributed. So let's get right into it. First, quantity stays exactly as is. Some of my 3s have been getting a little rough looking. So minus this number plus, changing sign, 8x to the fourth minus 11x squared minus x. I kind of don't like having to do that, having to look back and forth at it. I like when it's above, but that's okay, save me time. X to the fifth, 4 minus 14 is negative 10. X to the fourths, we have just that one. X cubed's just this one here. Couple x squareds, negative 9 minus 11 is negative 20. An x term here and a constant term there. Sprinkled here, there, everywhere, all combined. We get our good practice. These are, I hope you feel really comfortable on these. I hope you're not over relying on my video with this, at least after you've done a couple of them, that you feel right with these. You do want to feel comfortable. You know, I don't blame that they do several of these types of problems. I don't feel they're doing things significantly different in each problem. They just kind of are what they are. Sometimes things cancel. Ooh, sorry, I almost spoke over that. Sometimes things cancel, yes, and all that. But it's not like they're doing more quantities. There's only 2 quantities at a time, so nothing's really confusing there. Hey, 8 minus 9 is negative 1, by the way. I'm going to talk over this problem as I do it. But, you know, one thing that's really nice that they're enforcing, or, you know, as they're doing this, is hopefully you're getting just good on just the idea of combining like terms. That, you know, the degrees aren't increasing here, but when we start multiplying, you know that they will. Furthermore, that these quantities are separated by addition or subtraction, which means we're not distributing like FOIL. We're not doing that each term in one quantity by every term in the other quantity. We're just changing the signs and stuff. It gets lost when we start doing multiplication. Some people actually miss that. And honestly, if I messed up number 13, I wouldn't know because I'm talking over what I'm doing. But, you know, just do know what you're doing for each problem in each type. And don't let one type of thing leak into another as you learn it. So I changed all those signs, changed that sign as well right there. So anyway, just make sure you get the practice in. Whatever your teacher assigns for you, great, do it. If you want to practice extra, hopefully you're following along and making sense of it. Anyway, that's a cubed right there, so that's negative 6x cubed. No other squareds other than this negative 9x squared. Couple x's, 3x minus 2x is 1x. 11 plus 9 is 20. Got a lot of 11s and 9s combining together lately. Okay, that was the first good set of those ones. That took about 17 minutes for about 12 problems. So, okay, decent clip. It's probably going to go slower, though, as we mosey along. Number 15. During a recent period of time, the numbers in thousands of males M and females F that attend degree-granting institutions within the United States can be modeled by this and that. Where T is the time of years, write a polynomial to model the total number of people attending degree-granting institutions. Interpret its constant term. So we're going to do M plus F, males plus females in this case. We're going to add 19.7 T squared, 310.5 T, and 539.6. I'm going to do this one vertically just for room and because we haven't done it yet. Plus 28t squared plus 368t plus 10127.8. I'm going to use the calculator for some of these as I need to, especially that last one. I don't care to try and get that number right the first time. This first one I should be able to do okay. That's 47.7, I believe. T squared. These are like terms, by the way. This one I think looks okay. 678.5. Let me know if I messed up. Plus, okay. Can I do that one? I can listen. I can do this kind of math, right? 4 1 7 1. I haven't done this in forever like this. 6 7 1 like that. All right, that was hideous. Okay. I believe this is our new model for all of the males and females for, what was the time period? Where's T? T is time in years. So during a recent period of time. So this is in thousands of males and females. So they said, interpret its constant term. Interpret its constant term. Remember, this is in thousands. So there are 17667. Now for thousands, it would be 400. Okay, there are this 17,667,400 males and females, people, I guess, males and females that attended Or there were. This is a past tense thing for the constant. This is when time was 0. That attended degree granting institutions in the United States when this period of time began. Right? That's the constant. When time is 0, it's that. Remember, it's in thousands of people. Okay, that was a continuation of the addition of things. Let's look at number 16. Maybe this is going to be a subtraction. Oh, that's blue. A farmer plants a garden that contains corn and pumpkins. The total area in square feet of the garden is modeled by this expression. The area of the corn is modeled by that expression. Write an expression that models the area of pumpkins. Yeah, the area of the pumpkins is going to take the whole garden area, and this is one you definitely want to wrap around parentheses. And I will not use vertical for this one. Whole garden area minus corn garden area. You got to wrap it around parentheses. You got to do area minus area. This is garden minus corn. I should put a sub g minus a sub c for a sub p. All right. So rewrite it without parentheses. 2x squared minus 5x plus 4 minus x squared plus 3x minus 2. Distribute that negative. And now, standard form, you got x squared. Negative 5x plus 3x is negative 2x. 4 minus 2 is 2. This is the area for the pumpkin portion of the garden. Sorry for a little bit of mess, but that's it. I don't know what x is specifically, but don't worry about it. Number 17 to 24, they want you to find the product. So now we're going into multiplication of items, and we begin with a monomial, 7x cubed, times a trinomial, which is pretty straightforward. You are distributing 7x cubed into here. And I'm only going to show this once. Maybe on the second problem, I don't know. But 7x cubed is going to multiply by 5x squared. Then 7x cubed is going to multiply by 3x. Then 7x cubed is going to multiply by 1. 7x cubed times 5x squared. You do 7 times 5, and then you do x cubed times x squared. Those exponents add. You get x to the 5th. They do not multiply. It's not x to the 6th. 7 times 3 here is 21. Don't write x cubed. X cubed times x to the 1st is x to the 4th. 7x cubed times 1 is 7x cubed. You know, one thing that you're going to start to get used to is, let's say you do write this 3. Say you write this 3. First of all, don't finish the answer like that. You should actually combine these terms. But why would two terms be alike here when they weren't alike here? 3x plus 1 weren't alike. Why should these two be alike? They shouldn't. This should be 1 degree higher. These were degrees 2, 1, and 0. Now they become 3 larger. They're degrees 5, 4, and 3. So that's one of those things that's a good double checking standard for you. A monomial times a trinomial should always be a trinomial. Always. So let's keep that in mind. This is going to be a monomial times a quadrinomial. It should end up being a quadrinomial. Now we got a negative that's distributing into here. It's a good time for them to bring that one up because that means all these signs are going to change. Guess what? These were all positive. Well, these were all positive. Guess what? Now they'll all be negative. So this time I won't show the extra step here, but negative 4 times 11 is negative 44. X to the 5th times x cubed is x to the 8th. Add those exponents. Negative 4 times 2 is negative 8. X to the 5th times x squared is x to the 7th. Negative 4 times 9 is negative 36. X to the 5th times x is x to the 6th. Negative 4x to the 5th times 1 is negative 4x to the 5th. So all of the signs turn negative. There's the distribution of negative 4x to the 5th into each and every one of those terms. You do coefficients multiply together, variables multiply together, so their exponents add. And there you have it. They stay away from binomials times binomials. Foiling was so IM2. And even though you probably did some of these ones in IM2 here as well, they got to give them to you. But foiling, that was so IM2. Binomial times binomial. Not truly. We're going to have to do those at some point. But they're not setting you up with the problems right here. I would have loved some on drill and kill. I'm generally more of a fan of doing binomial times trinomial. Like, I like the look of number 20 more than number 19. But I'll do with it as it's written. I'm going to multiply. Actually, I am going to go this way. I'm going to multiply negative 2x by these three terms, just so that arrows can align. I want you to see them. Negative 2x times 5x squared is negative 10x cubed. Negative 2x times negative 4x is positive 8x squared. A lot of people will put 8x there. A lot of people, or negative 8x. That is squared. You just got off of combining like terms. Negative 2x minus 4x is negative 6x, right? But multiplied is 8x squared. Oh my gosh, a lot of people will do that. You who are watching right now are likely to possibly do that. Even after a warning, you'll go back later and do it. Anyway, I'll overemphasize that quite a bit. Now let's do 3 times those 3. 3 times 5x squared, 3 times negative 4x, 3 times 6. This is where I'll sometimes do the vertical thing. I'll put like 3 times 5x squared, but I'll put it with the x squareds, right? That's plus 15x squared. Align those. 3 times negative 4x is negative 12x. 3 times 6 is 18. Now I'm adding down these lists, but it's always addition. Negative 10x cubed combines with nothing. This is 23x squared. Remember those, remember these don't increase. This is negative 24x. Those don't increase. And plus 18. See, that's where someone's prone to make mistakes, right? You learn one thing, you try and apply it to the next thing, or you learn something new and you try and apply it to the old thing. That's where mistakes can be made. Be very, very careful. One little slip up makes the problem wrong. And if I'm grading this, if it's a test and I'm grading it, I get the wrong answer and I have to hunt for where you made a mistake. Don't make mistakes. Other teachers might go like, you got it wrong, you get a 0. I look for partial credit, so it's a little different. I like to give feedback. The majority of mistakes come from ignoring negatives and not increasing degrees of things when you multiply them. I mean, those are among them. Anyway, negative x squared times 2x. So here's the thing. The negative x multiplying these will all increase these by 1 and change their sign. That's it. So see the 2x squared, it'll be negative 2x cubed. See the 5x, it'll be negative 5x squared. See the 8, it'll be negative 8x. Boom. Now negative 3 multiplies by these. A little different. The squared and x stay the same. It's just 3 times larger. Change the sign. Negative 6x squared, negative 15x, negative 24. I know that you were just multiplying them, but sometimes you like to look at a pattern and go with it as fast as you can. Anyway, combine like terms. We get negative 2x cubed. The x squareds combine to make negative 11. Everything's negative here. Negative 23x and negative 24. It's a negative day, indeed. Number 21 is now a trinomial times a trinomial. There are different methods for which you can do on these, and I'll show you, or strategies. I'll show you one of them on another problem. It's the box method, basically. But x squared needs to multiply by these 3. I'll just write it like that because the arrows can get a little, confusing looking. I got x to the 4th minus 3x cubed minus 5x squared. Now negative 2x is going to multiply by these 3. Don't forget the fact that it's a negative each time. So that becomes negative, I'm going to line them up, negative 2x cubed plus 6x squared. That's the time they always forget it. Minus 10x, or plus 10x. And then I have negative 4 multiplying with those 3 is negative 4x squared plus 12x plus 20. Okay. Combine like terms, go down the list if that's the more helpful way for you. So you get x to the 4th, negative 5x cubed. Negative 5 plus 6 is 1, minus 4 is negative 3. 22x, plus, and then plus 20. See, whenever I do that vertical stuff, I seem to forget to write the number. I did that before too, right there. Yep. I'm not big on the vertical thing. I'm not saying it's bad. It's just not something I practice. And if I don't practice something, I'm prone to make a mistake more. Okay. Let's do this again. This time I'll do it linearly. Here's the thing. You get 9 terms, so writing them all in a line can get a little long. And then you're also trying to look for where things are when multiplied. All right, 3x squared multiplies with negative 4x squared. You get negative 12x to the 4th. 3x squared times negative 2x is negative 6x cubed. 3x squared times negative 1 is negative 3x squared. Now x times negative 4x squared is negative 4x cubed. It's going to be these, but 1 degree higher, right? Negative 2x squared and negative 1x. Negative 2 times negative 4x squared is plus 8x squared. Negative 2 times negative 2x is positive 4x. Negative 2 times negative 1 is positive 2. Okay, combined like terms, I see 1x to the 4th term here. X cubed terms, I see 1 right here and right here. That's negative 10x cubed. Negative 3x squared minus 2x squared is negative 5x squared plus 8x squared is 3x squared. X terms, negative x plus 4x is 3x, and then a lonely 2. Maybe that cross out thing would have been better off for you. Maybe, maybe not. Not quite sure. Number 23, I want to show you this box method thing. You've probably done it before, but let me write out the original problem. It's basically doing an area thing, like a length times width or base times height, however you want to put it, but you separate the components of the length and width by these separate terms and multiply in those areas. So what you could do is like this. Draw yourself a 3 by 3 grid, because that's how many terms are in each bit. Tic-tac-toe style. We can get 3x cubed, negative 9x, and 7. And then x squared, negative 2x, and 1. And then multiply within these inside here. 3x cubed times x squared is 3x to the 5th. Times negative 2x is negative 6x to the 4th. And then there's 3x cubed here. I made this kind of small. I apologize. This is negative 9x cubed, positive 18. I don't know why I wrote the plus there. Positive 18x squared. And negative 9x. And then 7x squared minus 14x and 7. There are 3 things I like about this one. One of them will not show up on this specific problem because this one was cubed instead of squared. I'm not going to bring it up. The 2 things I like about this mostly for others. Well, one for others that I like is that it tends, you tend to remember the negatives more. That negative 9, you won't forget to distribute in the other terms as much. You might only write it the first time. You might write it as a minus and then 9x times whatever and forget. But it gets you to remember the negatives a little better. The other thing is it's a little more condensed in overall footprint. Instead of writing it as a long stretch like this, it's a little smaller here. Now, you still have to add the results of whatever's here. So I'm just going to find things, cross them out when I find them. I have the x to the 5th as the leading term. So that's 3x to the 5th there. Then we'll find the 4th degree ones. It's just this one, negative 6x to the 4th. Get rid of that. And then the x cubes, I got these 2 here, 3x cubed minus 9x cubed. And then 8x squared, or 18x squared plus 7x squared. Kind of running out of room even still here. Let's bring it down. And then negative 14x minus 9x. And then 7. Now, I don't know if you noticed here. It was the other thing I was going to mention. It kind of does it, but not really. There are some things that are diagonally kind of woven together. Like this one was on its own. This was on its own. These were kind of separate, but then these were together and these were together. There's a nice diagonal interweaving that these will generally have, especially when they have matching degrees. If this was squared, you would totally see an alignment like this, and then these, and then these, and these, and that, where they kind of show up. It's really nice when that happens. That was not the case here because that wasn't squared. Number 24. I think I'll go back to conventional for it. I want to kind of work faster. But anyway, that's a method for you. Okay. Here we go. What kind of speed can I operate at here? First term, we got 4x to the 6th, and then 12x squared, or 12x to the 4th, and then 16x cubed. Now, with negative 8x, we'll get negative 8x to the 5th, minus 24x cubed, minus 32x squared. Running out of room, so I'll just write down here. Then we got minus, see, I should have used the box method, minus 2x to the 4th, minus 6x squared, minus 8x. Let's just hope I can see everything how it is. I'll put equals here so you know. 4x to the 6th, that's the only one of its kind. Any x to the 5th? Yes. This minus 8x to the 5th here. I'll cross out as I go, though, so you can see them. X to the 4th. 12x to the 4th minus 2x to the 4th is 10x to the 4th. Got an x cubed here and here, so that's negative 8x cubed. Negative 32x squared minus 6x squared is negative 38x squared. And minus 8x. So I just showed a lot of different versions of things you can do. Hopefully you kind of found your calling, or you already knew what to do, and hopefully I didn't make any mistakes and all that kind of stuff. All right, let's go to numbers 25 and 26 on error analysis. The first one is a subtraction sort. So let's correct the error. Let's see how often students make this error. This is good. This is bad. So what they did here, they did not distribute the negative. This negative only applied right there, and it didn't distribute the rest of the way. So on number 25, and of course we have to correct it, so we got to do the problem. They did not distribute the negative into all three terms of the second quantity. It only applied to the first term. Big no-no. That's what the parentheses are for, making sure that it's the entire quantity being subtracted. So the original, I'm going to keep the original. I'm not going to rewrite the original with parentheses. I'm going to rewrite it after parentheses. So when you distribute that negative, the first quantity was fine, x squared minus 3x plus 4. This will be minus x cubed, but then we should have minus 7x plus 2. And now, I'm sure when they combine like terms, they got their number right, but let's look. Negative x cubed, they even wrote it in standard form. Negative x cubed, there's just an x squared. Negative 3x minus 7x is negative 10x, and then 4 plus 2 is 6. Instead, they had a plus 7x here to make that 4x, and then 4 minus 2 was 2. So the last two terms changed. Number 26, the big no-no of the bunch. If I were to assign problems for homework, I would absolutely assign this one. And I'd probably assign it the next day too, and the third day, and everything like that. This is just wrong. This is ill. This is not correct. Plain and simple. Plain and simply, you do not distribute an exponent, and distribute's the incorrect term to use for that anyway, because distribute means multiplication, but you do not distribute an exponent into multiple terms separated by addition or subtraction. Remember, exponentiation means the number of times something multiplies to itself. Now, there's more than one way to write this thing out, but the first one I want to bring about to all students is that this cubed means this times this times this. It takes significantly more work to work out. Now, I'll show it two different ways to confirm that we're getting the right answer, as we're probably jumping into cubics as a whole. This is probably the lead into it, and it says, all right, here it is. So method number 1 is being applied right now. Method number 1. So what I'm going to first do is I'm going to expand. I'm going to get those two together. Now, this is a perfect square trinomial when you get that together. So really quickly, I'm going to write that as 4x squared minus 28x plus 49. And then we got to expand that out. So that becomes 8x cubed minus 56x squared plus 98x minus 7. Minus 28x squared plus 56, 112, 168, 28, 196? I'll see if that's right when I get to the other one that I have to do. Minus 340, 243? 343. Minus 343. All right, we'll see if this is right ultimately, but combine those. I got 8x cubed minus 84x squared. I might have made a mistake. Plus 294x minus 343. All right, let's see if that was correct by doing method number 2. Method number 2, for me, will be the perfect cube thing. 2x minus 7 quantity cubed is, you do this 1, 3, 3, 1 thing. You do 1 times 2x cubed times negative 7 to the 0 plus 3 times 2x squared times negative 7 to the first power plus 3 times 2x to the first power times negative 7 squared plus negative 7 cubed. All right, 2x quantity cubed is 8x cubed. 2 squared, here, I have to show more work on this one the first time you're seeing this, but this is 3 times 4x squared times negative 7. Let me start writing that stuff below. 3 times 7 is 21 times 4 is 84. So this is minus 84x squared. And then plus 3 times 2x times 49. 2 times 49 is 98. 98 times 3 is 294. So that's plus 294x. Okay, good. I got the right number. Negative 7 cubed is negative 343. Okay. So you get the same answer regardless because you got the right numbers there. So I don't know which one's better for you, worse for you. You still know how to expand that and work that out. This is one we're going to be doing for bigger numbers though anyway, so get ready to do them. I don't know if it's right now, but get ready to do them soon. Find the product of the binomials here. So on these sets here, this is where I'll do 2 at a time, and then I'll do the other sets. So x minus 3 times x plus 2 times x plus 4. I'm always going to do the last 2 ones first because I like a binomial out in front. So let's do x minus 3 times, and here's where we get to FOIL, by the way. This is our FOIL fun. X squared plus 6x plus 8. I'm not going to go slowly on that, but that's x squared plus 4x plus 2x plus 8. 4x plus 2x is 6x. Okay? I will be going quickly on those binomial expansions, foiling. That was so IM2, guys. Yeah, 95 problems, right? Now, we expand this one. So x cubed plus 6x squared plus 8x minus 3x squared minus 18x minus 24. And that becomes x cubed plus 3x squared. All right, so there's your final after you do combining of like terms and such. Now that we've done a bunch of those, I really want to get into like, all right, we get to speed through it. Powering through. This is a drill and kill, right? There's a drill, let's kill it. Number 28. And a lot of these are kind of same-ish, right? X minus 5 times x plus 2 times x minus 6. Let's begin with the last two. In FOIL, that's x squared minus 4x minus 12. And we keep going. X cubed minus 4x squared minus 12x. And then negative 5 times these. Negative 5x squared plus 20x plus 60. Remember, negative 5 multiplies into them. Therefore, they change sign. They're positive. X cubed, negative 4x squared minus 5x squared is negative 9x squared. This is plus 8x plus 60. My only concern, and this is with me recording the video, is maybe you're following along, and I'm going fast. I'm talking fast. I'm going fast. You're like, wait, slow down, whatever. I get it. There's kind of this trade-off, right? How often can you press the pause button? Can you do me in slow-mo on 0.5 speed, right? Can you have me play back that speed? It just depends on what you want to do on those. For me, I'm doing the problems. I can do them in silence. You can check against it. You can do like, let's time ourselves go, that kind of thing. A lot of different things you can do on them. I don't know how people choose to study with my videos. I do them for solution guides. I'm going to distribute these. So this is going to be 12x squared minus 9x plus 4x is negative 5x, and then minus 3. And we keep going. X times 12x squared. Remember, these ones, when x multiplies by these are nice. When x multiplies by these, just increase. 12x cubed, negative 5x squared, negative 3x. These change sign, negative 24x squared plus 10x plus 6. So we end up getting 12x cubed minus 29x squared plus 7x plus 6 when all like terms are combined. See, doing things like box method and writing down vertical columns and stuff, for me, gets in the way of my level of efficiency I want to go for. What I would stress to all students learning some things is, you go, how do you go that fast? Like, oh, you can go that fast because you're a math teacher. But why are you a math teacher, right? That's not like philosophically or morally so, but why are you trained? Why? How come you have the ability? You push the envelope. You push toward working these as fast as you're able to in some ways. Okay, I'll leave the 2x plus 5. Actually, let's do this. Let's leave the x minus 2. I really like the x being on that one. I'm good on foiling. I'm going to foil these two together if that's right. I'll even put it in blue. So I got 6x squared plus 8x plus 15x plus 20. And now I really like that x in front because this next one they multiply super fast. Just take these and raise it by 1. I have to sneeze. Excuse me. Negative 2 times these. Okay, now I combine like terms. And so that was a strategy, right? That was a strategy that I employed. There are a lot of different times that you'll see me do strategic things like that. I don't know if it made it faster or not. Made me feel better about it, though. That's a for sure. And listen, I hope I haven't messed up any problems. I'm talking through these. Sometimes I'm not focused fully. I hope I got that one finished right. Now, number 31 has something else that I'm not a fan of here. I can, and same with 32. So 2 of these, listen, I really, when it comes to speed, as I mentioned, my speed comes from familiarity. I don't like being unfamiliar with things. Guys, what's unfamiliar about this problem here? The middle quantity. The x is last. It's also negative. I don't love that x being negative. I have a remedy for you here, and it's this. Factor the negative out. Put it on the outside. I don't want it there. I'll be fine here. I'll even put this term in front. I'm going to write it as 2x minus 5. I factored the negative out. The 2x is positive. Now the 5 is negative. I'll rewrite this one next, and then this one here. It's a preference. Now, I'll leave the negative till the very last step. I'll leave the negative till the very last step. I want these to be as they are up until then, if that's cool. So this is going to be the same. Do you have to do it this way? No. This is a personal, I'll get through it better, faster. I feel like I have a better shot at getting it right kind of thing. That's just my personal thing. If you have yours, there, be efficient where you can. I feel like I'm sinking. Just a little bit. All right, let's FOIL this guy here. Plus 3x minus 16x. And then minus 4. All right, negative stays on the outside. After this one, I'll bring it in probably. All right, 24x to the fourth, or to the third. Minus 26x squared. So 8x. Okay, negative 5. Minus 60x squared plus 65x plus 20. All right, now everything's going to combine. Can I do the negative at the same time as I combine things? Let's try it. The only x cubed is the 24, so I'll make it negative 24x cubed. Negative 26x squared minus 60x squared is negative 86x squared. Let's make it positive 86x squared. Yeah? Does that make sense? Negative 8x plus 65x is 57x. Make it negative 57x. And plus 20, make it negative 20. You could do an extra step on top of it without it distributed and then distribute it. It's up to you. Guys, I feel the same way in number 32. Not only that, I think I'm going to benefit from doing it this time. So I'll write the original problem, 4 minus 5x, 1 minus 2x. I mean, I think I'll benefit more than not having it the other way. Because here's the thing. If I factor out these negatives, remember, I want to make this thing 5x minus 4. I want to make this thing 2x minus 1. I can't just switch them, though, right? What do you have to do? You have to factor out a negative. But if I factor a negative out of this one, remember, it's a negative 1 times negative 1, that's positive 1. I factored negatives out of 2 of them, and it's left with a positive. So there's my benefit. I don't even have a negative on the outside. I don't have to worry about it. Now, that's not something that even the book would be preaching right now. Factoring doesn't come for 2 more sections. But I'm going to do it. We've done factoring in the past. Leave 5x minus 4 as is. Let's go ahead and FOIL this guy. We get 6x squared plus 4x minus 3x minus 2. And now we get to keep moseying along. 30x cubed plus 5x squared minus 10x. Then negative 4 distributes. We got negative 24x squared minus 4x plus 8. 30x cubed stands alone. 5x squared minus 24x squared is negative 19x squared. Negative 10x minus 4x is negative 14x. Pardon me. And then the plus 8 is its own thingamabob. Okay. Even with all the talk, I don't know. Tell me if you would have gone faster with it. I really don't like those things on that side. See, my speed is in my foiling especially. And having things more in that standard form, kind of descending, all that kind of stuff. So I really, 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 really am fast with familiarity like that. And by familiarity, I mean familiarity with problems that are normally like that. All right, number 33, reasoning. Prove the polynomial identity a plus b times a minus b equals a squared minus b squared. Then give an example of 2 whole numbers greater than 10 that can be multiplied using mental math in the given identity. Justify your answer. Okay. A plus b times a minus b. What did I just do? A plus b times a minus b equals a squared minus b squared. Let's do it on this side where we FOIL. A times a is a squared. A times negative b is negative ab. B times a is positive ab. Remember, just write them alphabetically. And b times negative b is negative b squared. Negative ab plus ab is 0. Those cancel out. You are left with a squared minus b squared. So that proves it. basically, that's why I will never do, and listen, I'm sure special cases are popping up next. That's why I'm never going to be doing the foiling on these guys. The middle terms are going to cancel out, and you're left with a squared minus b squared. So I'm always going to use that rule. I'm never not. I want you to know that right now. You can foil as much as you'd like to. I'm not going to. I'm going to use the difference of two squares rule. Now they said, give an example of two whole numbers greater than 10 that can be multiplied using mental math in the given identity. So, let's do, I don't know, let's make something up. Let's do 42 and 28. All right, 42 and 28. What you need to do with these is find out how far they are apart from each other, like average them. So 42 plus 28. Well, there are a couple things you can do. You can either average these numbers or you can find half the distance between them. But 42 plus 28 divided by 2 is 70 over 2, which is 35. That means 35 is the middle value of these, and it's 7 apart from each of them. We should know that as well. 42 minus 28 over 2 is 14 over 2, which is 7. So 35 and 7 are the two numbers you use from here. 42 times 28 is also the same as doing 35 plus 7 times 35 minus 7. That's the basic idea. Now that means we're going to do 35 squared minus 7 squared. 35 squared is 1225. 7 squared is 49. I'm glad I landed on a number I knew the perfect square for. I don't know 34 squared, but I do know 35 squared. So that kind of lucked out. I don't know 1225 minus 49. It's 1176. So that should be 42 times 28. But Mr. Robinson, I can do 42 times 28, where I do the 6 here and carry the 1 and get 33, and then do the 0 and I get the 4 and I get the 8 here, and then I add down the list and I get the 1176, and there's the answer. I know. The idea here is, could you do that mentally, meaning store all those numbers in play? I'm better off, assuming I know 35 squared, but that's the thing. You need to know your perfect square for your number. I'm better off doing 1225 minus 49 than I am storing those numbers in my head. That's just me. Yeah, but Mr. Robinson. There, you know what? We're showing that the identity works. Among anything else, we're showing the identity works. They're not saying you got to do it that way. Nobody is. Number 34 on number sense, however, might ask us to do some stuff. You have been asked to order textbooks for your class. You need to order 29 textbooks that cost $31 each. Explain how you can use the polynomial identity, a plus b times a minus b equals a squared minus b squared, in mental math to find the total cost of textbooks. Oh, they said mental math for this last one. So this time I'm going to do it mentally, okay? Let's see if we can do this. Check this out. So number 34. So first of all, how you can use it to work it out. The idea is we're going to do 29 textbooks times $31 per textbook. Now the answer will be in dollars. That'll be in dollars, right? So here's the mental math. 29 times 31 is also 30 minus 1 times 30 plus 1. So the mental math I'm going to do is 30 squared minus 1 squared. That's 900 minus 1, which is $899. That is significantly faster than, but Mr. Robinson, I could use 31 to 29 and do the 9 and do the 2 and add the 0, and then you get a 7 and carry the 2 and get the 8, and then you add these all together and you get 9 plus 9 and 8 and 8 and 9. Right? That was significantly faster this time, recognizing that it is what you can do and kind of working off it that way. Those are the little kinds of things that work it out. By the way, I'll leave this up here so that we can confirm that's the right answer. So $899 in total. I was asked to order them. Do I have to pay for that? I hope not. It's a lot of dollars. All right, 35 to 42, find the product. These are special case ones. Guys, I'm going to work as fast as the Dickens will allow me regarding the special case that's involved. X minus 9 times x plus 9. Now, I will show you the routine. This is a squared minus b squared, so that's going to be x squared minus 81. Am I going to do that each time? No. Am I going to do it this next time? No. You know why? It's not a difference of two squares. This is a perfect square trinomial. This is a square of it's a square of a binomial. But m plus 6 squared, I'll show you this one. You square the first term. This is a, even though I've done these quite a bit so far this year. This is a squared plus 2ab plus b squared. So you do square the first and last terms, right? M squared plus 36, but then you got to double 6m. You get 12m, right? So anytime I do something once, I'm not going to do it with the work again. I'll just probably say it out loud and go off it. 3c minus 5 squared is technically a different kind of question because there's a negative this time, but it still is the 2ab thing. And it's a little different because you have 3c instead here. 3c minus 5 squared. You got to square 3c. You got to double the product of 3c and 5, but you subtract this time, and you got to add 5 squared. Now, what you can also do, if you forget the subtraction here, here's what you can do. Turn this into addition, make these ones negative, and go off that. And I'll do that this time. This is 9c squared. You got to double negative 15c, so that's negative 30c. And here you get plus 25. Even if this is negative, you still square it and it still turns positive. There's no change on that. Perfect square trinomials have an added constant term. It's number 37. Okay, guys, number 38 is the next difference of two squares. I'm not going to show the extra work in between, but I'll say it. This is a minus b times a plus b. That'll be a squared minus b squared. You got to remember, though, when you square 2y, you got to square the 2 as well as the y. So 2y quantity squared is 4y squared minus 5 squared, which is 25. That's the result. Number 39 is a perfect square trinomial, as we've already seen with a sum. So I'm going to go straight into it. 7h plus 4 squared. First we square a. 7h squared, quantity squared is 49h squared. Now we're going to double the product of 7h times 4. We're going to double 28h. That's 56h. Then 4 squared is 16. That's how fast these can go. I mean, they can go faster. I still explained through it, but that's how fast these can go. Now we have 9g minus 4 quantity squared. Again, we saw this kind of number 37. There was the minus. This is where maybe you got to remember that the minus is in play if you're going to go at that kind of faster speed. 9g quantity squared is 81g squared. We got to double the product of these two with the minus. That's minus 36g doubled. It's minus 72g. Then plus 16 plus the 4 squared. Okay? Those are special cases. Listen, they are expected. In IM3, they are expected that you're able to do those with ease, with rapid pace, because we're using them for bigger parts of problems, if that makes sense. Now, we just saw some instances of ones being cubed, but this is where we're going to get deeper into the binomial expansions as a whole. This is where you have, let me write this above it. A little bit above it. Excuse me. A plus b quantity cubed is a cubed plus 3a squared b plus 3ab squared plus b cubed. There are a couple things involved. In Pascal's triangle, you have 1, 3, 3, 1. And a is going down, 3, 2, 1, 0. B is going up, 0, 1, 2, 3. Those are things to probably keep in mind when you're doing this. There is more than one step you generally got to do on these. Even I'm not going to do this in one step. So we are going to cube 2k. Leave the 6 alone. Plus 3 times 2k gets squared. Whoops, 2k gets squared. 6 is raised to the first power. Plus 3 times 2k is raised to the first. 6 is squared. Plus 6 gets cubed. Okay? 2k quantity cubed is 8k cubed. I'll show the intermediate step right here. Sometimes I won't, but 2k quantity squared is 4k squared, and got to multiply that by 6 still. You can do like parts at a time. If you want to do 3 times 6 early on, you can. You know, it's up to you. Oh, this 6 is squared, sorry. Plus 3 times 2k, like I could turn this into 6k right now if I wanted to. And 6 squared is 36, plus 6 cubed is 216. So yeah, we still got to work out those middle guys. 3 times 4 is 12, times 6 is 72, so we get 72k squared. 3 times 36 is 108, times 2 is 216. And there's another 216 here. So that's the final result of that one. Probably the fastest way to go about it. There are some steps in work that I'll probably skip or optimize a little bit better as I work along them. Now, number 42 is the same. There's a minus involved. I am going to treat the 3 as the negative. I think that's the safer play. You would have to remember to change signs otherwise each time. It's kind of up to you. I'd rather make the 3 negative. So, and just realize why they change sign each time. 4n gets cubed, and then 3 gets multiplied with 4n being squared and negative 3 to the first power. And then another 3 times 4n to the first power and negative 3 gets squared. And then negative 3 gets cubed with no 4n. Now 4n quantity cubed is 64n cubed. This time, let's work this out in kind of a faster pace. I got negative 9 times 16, right? 4 squared. So that's negative 144 n squared. And then 9 times 12 is 108. And then minus 27. So hopefully you saw what I did there. I'm trying to point to the parts that we had. That was, again, 16 was 4 squared. 3 times negative 3 was negative 9. So negative 9 times 16. I mean, you might need to use a calculator for that. But negative 9 times 16 goes there. Negative 3 squared was 9. 3 times 4 was 12. 9 times 12 is 108. That's where I'm working off that part in speed. I'm getting a writer's mark thing on my finger it's getting a little painful. It's like a blister almost, if you will. All right, there are those ones. Now we're going to use Pascal's triangle to expand the binomial here. Now they say see example 7. What I'm going to do is I'm going to build Pascal's triangle for you guys. You might have seen it previously. Row 0 has the number 1. Row 1 has 1 and 1. Row 2 has 1, 2, and 1. We're going to add these. 1 plus 1 is 2. 1 plus 2 is 3. And symmetrically, we get 3 and 1. Those are the numbers 1, 3, 3, and 1. Row 4 has 1. 1 plus 3 is 4. And 6, 4, 1. And then add these. 5, 10, 10, 5, 1. I'm going to do one more. I don't know if we need it. 1, 6, 15, 20, 15, 6, and 1. Pascal's triangle is used in binomial expansion based on the row that you have for things. Keep in mind, this is row 0, 1, 2, 3, 4, 5, and 6. Okay, so those are the rows involved. This is based on whatever power we raise this to. See if you keep this in mind. See if you heard me on the lecture portion. See if you can follow along. If you didn't, let's try it. We have 2t plus 4 quantity cubed. Now, we just did a cubed thing. It's not like this is going to be new. We just came off of one. But let's follow along. Row 3 is going to have 4 terms. The first term, I'm going to write it with this in mind. The first term is 1 times 2t gets raised to the 3rd power, and 4 gets raised to the 0 power. Remember, we just came off of this, but I'm going to expand it in the way that hopefully it makes best sense and how you can do it each time and not ever miss anything. Plus 3 times 2t is now raised to the 2nd power, and 4 is raised to the 1st power. Yamin. Plus this 3 times 2t is raised to the 1st power, and 4 is raised to the 2nd power. Plus, I ran out of room, plus this 1 times 2t raised to the 0 power, and 4 raised to the 3rd power. So that's the more expansive version of using Pascal's triangle for that. What I think I'm going to do, by the way, guys, is I'm going to shrink this guy, not like that. I'm going to shrink this guy up and keep it in my pocket for future problems over here. We're going to take it, shrink it. I don't know if you can still see it. If you're on your phone, sorry. I'll just kind of keep it for future problems here. Maybe I can expand it as I go. I just want to, it's like an Ant-Man thing, right? Honey, I Shrunk the Kids, whatever. Anyway, so from here, 1 times anything is nothing. Listen, 4 to the 0 is 1. That would go away. 2t to the 0 is 1. That goes away. 1 times anything is just that thing. Those go away. That's why we're only left with 2t cubed on that scenario. So that's 8, or 2t quantity cubed. So that's 8t cubed. This is where you got to do that. And, 4 to the 1st power is just 4. You can ignore that. 2t to the 1st power is just 2t. That can go away too. I'm looking at the coefficients. 2 squared is 4 times this 12 is 48. So I get 48t squared. I'm just doing this now all in the next step. Plus 4 squared is 16 times this 6 is 96. So 96t plus, and 4 cubed is 64. So there's the final result of that guy on that problem. All right, here's my pocketed Pascal's triangle. Let's take a look at number 44. Now, number 44 is having this thing squared. Listen, we've done perfect square trinomials. We're just looking at Pascal's triangle to work it out so we can make sense of the ones where we have to expand beyond squares and cubes. So let's see how it works out here. 6m plus 2 quantity squared. This time I will slow down. Looking at this miniature Pascal's triangle and expanding it just a little bit for our eyes, we're going to look at row 2. Row 2 has 1, 2, and 1. So we're going to do 1 times 6m to the 2nd power times 2 to the 0 power plus 2 times 6m to the 1st power times 2 to the 1st power plus 1 times 6m to the 0 power times 2 to the 2nd power. As you can tell, the first term goes 2, 1, 0. The next term goes 0, 1, 2. They increase and decrease that way. I bring these up again to remind you of not only is this going to now be, remember 1 times anything is just that thing, 2 to the 0 is just 1, and this is just 1, and this is 1, first power doesn't matter. Now look what this looks like. This looks like 6m squared plus 2 times 6m times 2 plus 2 squared. Where have you seen this before? This is a squared plus 2ab plus b squared, right? So it is that perfect square trinomial thing. I mean, literally straight up. So you get another instance of that. Maybe Pascal's triangle will lead you to the way to that. However, that would be a lot of extra work to get binomial expansion of a squared product, or of a squared set, squared binomial, when you could probably just FOIL at that point. Anyway, that's the result of that one. Okay, let's keep our little pocketed guy and keep moving him forward. Now I think is necessary to look at for these next couple problems here as we go to the 4th power. Even for me, it might be worthy for me to remember what numbers go there, if you know what I mean. I don't really know where to put this. I don't know. I guess I leave it here and just leave some space. But the numbers we're going to look at here for number 45, it's raised to the 4th power now. We're going to look at the row 4, which has 5 terms. We're going to look at the numbers 1, 4, 6, 4, 1. At some point you do them enough, maybe you'll remember those numbers. Like I remember 1, 3, 3, 1. I remember 1. Listen, I can build Pascal's triangle in my head for the most part if I know the numbers before. But it just depends. All right, let's see. 1. This is the last time I'm probably going to use the numbers that go alongside the thing. But 1. And then these things are here. This is to the 4th power. That doesn't look like a 4. This is to the 4th power. This is to the 0 power. Remember, these have to add to 4. And then plus 4, right? 1, 4, 6, 4, 1. So 4, 2q is cubed. Negative 3 is to the 1st. Plus 6, 2q is to the 2nd. And negative 3 is to the 2nd. Plus 4, 2q is to the 1st. Negative 3 is to the 3rd, and plus 1. 2q is to the 0, negative 3 is to the 4th. So you can see at some future stages, guys, I am not going to be putting 1s in there. I'm not going to be putting things to the 0 power there. I'm not going to be putting things to the 1st power there. I won't put the first powers there either. Those are little remedies that will save me a little bit of time as I write them as they go along. Okay, maybe I will in reviews and such, but as far as this assignment, I feel like I've exhausted what I wanted to there. So 2q to the 4th is, or 2q quantity to the 4th is 16q to the 4th. Now, all these things, guys, there's only one single variable. This will have a q cubed in it. Next, we'll have a q squared. And you'll notice because that negative 3, this will change sign. So minus something q cubed, plus something q squared, minus something q, plus that last number, right? Whoops, I actually need the minus out here. So you kind of know that that's what's showing up. All that matters to me now are coefficients. I don't even care about the negatives. I know what's going to come up. So I'm looking at 4 times 3, which is 12, times 2 cubed, 8 is 96. So 96 q cubed there. 6 times 4 times 9. Let's do 6 times 4 is 24. 24 times 9 is 216. 4 times 2 times 27. 8 times 27 is also 216. And then 3 to the 4th is 81. So I believe that's the final results of this one. It's very, very possible I can make mistakes on these things, especially as I do mental math. Everything I'm doing setting it up is proper. I only hope I'm following through for you guys the right way. I trust everything I've done so far has been correct. Let's bring Pascal's triangle down for the next set. However, I'm going to give you a little more speed when it comes to the ideas of coefficients and the like. G plus 2 to the 5th power. All right, the numbers are smaller, which is kind of nice. So the first one is g to the 5th. Remember, it's 1 times g to the 5th times 2 to the 0. So g to the 5th. The next one, the g will be to the 4th, but I need the 5 here in the coefficient. 5 times g to the 4th times 2. Remember, 2 is to the 1st power. Plus 10 times now g is going to be cubed, and 2 is going to be squared. Plus 10. Now g is squared and 2 is cubed. Plus 5. G is to the 1st. Whoopsie. G is to the 1st and 2 is to the 4th. Plus 2 to the 5th. 1 times g to the 0 times 2 to the 5th. All right? That's a little less extra work to be had when all the ones and stuff are kind of just not involved. And it's really just ones that are not involved. G to the fifth plus, that's 10g to the fourth, plus 40 g squared plus 80, oh, g cubed, excuse me, g cubed plus 80g squared plus 2 to the fourth is 16 times 5 is 80, g plus 32. 2 to the fifth is 32. G, that's a lot. Two more, and they did these in examples. They have two variables in the product. That's really not going to change what we do. We're just going to double up what's there. But all right, number 47. This actually is going to have really small numbers as a whole. YZ plus 1 to the fifth power. Listen, we just did 1 to the fifth power. 1, 5, 10, 10, 5, 1. If you remember those numbers. First one, we got to do YZ to the fifth. So 1. And then 5 as this goes down in order. You know what you could do? Okay, actually, I'm not going to do it for this problem. But heads up, 1 to the fifth. Guys, 1 to any power is just 1. 1 to the x is 1, right? So do I need to write 1 here and 1 squared and 1 cubed? I'm not going to for the problem. I'm not going to. Guys, I'm not going to. 10, actually, I could do this without any extra work if I really wanted to, because this is cubed. That means I have to cube each of these. Another 10. 5, and then plus 1. That's where the 1 can go to play, right? This is 1 to the fifth power, whatever. But that 1 is there as it's not only 1 is the coefficient, times y to the 0, which is 1, times the 1 that's that term that's being raised to the fifth power. So all those together. So it's the same answer as before, only now we got to kind of expand this. Y to the fifth, z to the fifth, plus 5, y to the fourth, z to the fourth, like that. So it's just going to keep going. So cool on the smaller numbers. Thank you for those. Whoopsie, I missed a y. 10 y squared. Yeah, I could have done this without the step in between, I suppose. Very much so. Yeah, having the extra variables is just more to write. Doesn't necessarily make it a harder problem there. Okay, number 48 really looks to be more than the same. It's to the fourth power now. If you remember, those coefficients were 1, 4, 6, 4, 1. 1, 4, 6, 4, 1. And if you notice, this one's also a 1, which means I'm also not going to write the 1s here. There's one difference, and that's the minus. If you remember what happens with minuses, the signs alternate every time. Positive, negative, positive, negative, positive. That's what we're going to have. So let's see if we can do this in one step. Watch this. First term is n to the fourth, p to the fourth. Minus, that's the only thing the 1's changing, the minus. 4, n cubed, p cubed. Plus 6, remember, 1, 4, 6, 4, 1. 6, n squared, p squared. Minus 4, np. Plus 1. That should be the final answer of that one. There was nothing else to calculate because the coefficients were 1s, which is really nice. 1, 4, 6, 4, 1, alternating signs. There you go. This is still probably very new for you with that in mind, but I am still trying to give you the nitty-gritty of what it is we're making happen. We're more than halfway through the problems. I don't know if we're more than halfway through the time. The time's only been an hour and a half, and that's not even counting the lecture. So we're pretty good on time. We'll see how it works. Find the nth row of Pascal's triangle, then expand the binomial. We had it. Was it 1, 6? Shoot. 1, 6, 15, 20, 15, 6, and 1. So n equals 6. That's the 6th row. We're going to do x plus 3 to the 6. All right, so this row is 1, 6, 15, 20, 15, 6, and 1. If you recall the following things. Number 1, there are 7 terms in the 6th row. One more than this. Number 2, there's symmetry, right? So if you know the build-up to it, then you can get down to the other side of it. All right, expand the binomial. So there it is, Pascal's triangle. I mean, it's no different than what we were doing before, so here we go. So 1x to the 6th plus 6 times x to the 5th times 3 plus 15 times x to the 4th times 3 squared. I'm just going to write 9, 3 squared, right? Plus 20 x to the 3rd times 3 cubed. I have to go to the calculator in a second. Plus 15 Let's put it next to the other 15. Plus 15 times x squared times 3 to the 4th plus 6 times x to the 1st times 3 to the 5th plus 3 to the 6th. Okay. That's what we're working off of there to expand. Okay? X to the 6th plus, that's 18x to the 5th. This is, I don't know, 15 times 9. 135 x to the 4th plus 2 times 27, 540 x cubed plus, is it, hold on. Is that it? 1215 x squared? I'm going to check that in a second. I don't know 6 times 2, 43. Well, let's see. What's 729 doubled? 729 doubled is, what's 29 times 3? 14. Oh, shoot. 30, 87. 14. Shoot, I just had it. 1487? No, I can't fit it. Plus 729. I want to fit this all in one line. Plus 729. I need to box it. I believe those numbers are right. I'm going to check on this old Magna Carta right here. 15 times 81. 15 times 81. Yes, 1215. Okay. All good. Looking good. Okay. Oh, I didn't check that one. 6 times 2, 43. I believe that one's right as well. 1458. Oh my gosh. I got that one messed up. Oh, 729 doubled. What did I do? It's 1458. 14. I even forgot what I just wrote as the answer. Sorry. I think I said 87. I don't remember why I said that as the answer. Okay, that was the wrong number. My bad, my bad. Good thing I checked. Okay, number 50. I'm actually going to use the bathroom after number 52. Chug a little more water just to validate it. All right, n equals 7. Here's the thing. It comes after n equals 6 on Pascal's triangle. So even though I haven't built 7 yet, I can do it based off 6. I have 6 right up above. Ooh, this problem's going to take a little bit more to do as a whole in general. All right, building off this one up top here, we're going to have a 1, and then we're going to do 1 plus 6, right? 6 plus 15, 15 plus 20, and then it's symmetric the other way. 35, 21, 7, 1. Now, the numbers are going to get quite big on this one as a whole. So, here we go. The first one, the first term here. Now, I'm going to have to probably write 4 terms at a time on each line here. You know what I could do? I think I seem to remember now. Did I do them vertical? There was something that I remembered once doing when I was recording them that I said, you know what, that was better. Was it like, was it doing them vertical? I don't remember. I'll keep doing it this way. All right, we're going to start with 2s. That's not a 25, by the way. That's 2s to the 7th. I'm going to alternate signs right here and right now, as in you know the sign's going to alternate. So minus, and then 7 times 2s to the 6th. These are already going to be big numbers. And then times t to the 4th. Okay, there are 2 variables in here. You really got to be careful with that set. Plus 21 times 2s to the 5th. Oh boy, my 5s look like s's. Uh-oh. 2s to the 5th. I hate when they use s's. Times t4th squared, right? Minus 35 times 2s to the 4th times t to the 4th cubed. This is going to have a lot of work on it. Plus 35 times 2s cubed times t to the 4th minus 21 times 2s squared. Oh, I think that's what it was. I think because I had these, I wrote the same thing down. I copied and pasted it down a vertical line, and then I could write the numbers. I'm going to try that for the next problem. I know you can't do that. It's just going to be something I'm going to streamline and just show you and say what I was doing. I think that was it, but I'll check. T to the 4th to the 5th plus 7 times 2s to the 1st times t to the 4th to the 6th plus t to the 4th, or minus t to the 4th to the 7th. Remember, the t to the 4th was negative, so anytime it's being raised to an odd power is what's making the term negative. right? That's what's happening there. Now, 2 to the 7th is 128. So 128 s to the 7th will be the first term, period. Minus, this is a lot of stuff. This is 7. Now, the t to the 4th will stay after that anyway, but 2 to the 6th, actually, these will probably just get us the answers here. Oh, never mind. What's 2 to the 6th is 64. So 7 times 64, and then we have s to the 6th and t to the 4th, right? Just 7 times 64 has to happen there. 21 is going to have to multiply by 32 here. 32, s to the 5th. T to the 4th squared is t to the 8th, not t to the 6th. You multiply those when it's an exponent to an exponent. Or whatever. Minus 35 is going to have to multiply with 16. This is s to the 4th times t to the 12th. There's no rhyme or reason to my parentheses right now, but I'm not going to write more parentheses than I need to. Plus 35 times 8, s cubed times t to the 16th. These t's will get big. Not as big as some of these coefficients. Minus 21 times 4, s squared t to the 20th. Plus 7. Why did they do this to me? Plus 7 times 2, s times t to the 24th. That's a 4. Minus t to the 28th. Okay, last step. I still have to write them on 2 lines, I think. 128 s to the 7th. All right, 7 times 64. Go to the calculator. I just don't want to make a mistake. I didn't come this far, right? 448. Who would have known? Minus 448 s to the 6th, t to the 4th. Plus 21 times 32. Like, what? Use your difference of 2 squares, Mr. Robinson. Not when one's an even, one's an odd. That means the middle value is a decimal. It's a 0.5, so I ain't gonna do it there. Mr. Robinson, if you could do mental math with difference of 2 squares, why don't you do that? I can hear people saying, you know what's interesting about this? I'm gonna say it after I'm done. It has to do with standard form. Minus 560 s to the 4th, t to the 12th. All right. 35 times 8. I mean, what? A number? 280. I thought it was that. Because it's 70 times 4. 280. 21 times 4 is 84. I should be good the rest of the way. S squared t to the 20th. What's 7 times 2? All right. Here's the interesting part. Standard form should be in descending order of degree. Yes, the s's are going down in degree, blah, 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 but you should be adding the exponents to get the whole degree of your variables. This is of degree 7. This is of degree 10, 13, 16, 19, 22, 25, and 28. This is the highest degree term. This should technically be written first. I know it's the t variable, and I know it's negative. For standard form, basically, you should reverse the order. If you wanted true standard form, you should reverse the order. And honestly, that would have been realized initially. You would have reversed this as t to the 4th minus, or negative t to the 4th, I guess, plus 2s. I mean, that would have looked a little weird. But, you know, the t to the 4th immediately in the beginning wasn't, you know, standardized. So there's that. It's kind of up to you on whether you want to do that one. That one I've reversed standard form. I hope you're okay with it. And I'm sure the book probably would have kept it that way. But, and same with this one, right? See the a plus b squared? This will be reverse standard form again. Now, n equals 9. I don't have that one in my playbook here. So let's come up with what that is. Last one we had was, I'm going to build off 7. We had 1, 7, 21, I think. 21, 35, 35, 21, 7, and 1. Let's get 8. Row 8 is 1, 8, 28. To think, I don't remember these ones at all. 56, 70, 56, 28, 8, and 1. Now 9. This is going to be a lot of terms, guys. This is why I'm going to do the copy-paste thing that I was saying. Write it down vertically. 84. 84, 126. I don't even know if I've written this far down before. Hope I did it right. Should find it from the internet, be sure that's right. But anyway, so we're going to have 10 terms. We're going to have 10 terms. What I'm going to do is this. A and B squared. Okay. A and B squared. I'm going to go more toward the conventional route that I had before. I'm going to have this written, copied and pasted 10 times. We are going to use an infinite cloner and go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This will help me when it comes to the speed of my writing and everything else. Now, my Pascal's triangle numbers will go in front. 1, 9, 36, 84, 126. And then backwards. 126, 84, 36, 9, and 1. Okay, like that. What I should do, let me Google and confirm that those are the Pascal's triangle numbers. Triangle. Row 9. Row 9. 84, 126, 36. Yeah, those are okay. Those are the numbers. All right. Now here's the last part I got to do. Raise it to certain powers. This one will be raised to the 9th power and 0 power. Then check this out. 8, 7, 6, 5, 4, 3, 2, 1, and 0. And these are raised to 0, 1, 2, 3, 4, 5. Whoopsie. 5, 6, 7, 8, 9. I don't know if there was more speed involved with that, and obviously these have to add up and such. I still have more to do, but that helps conceptualize what we're doing more in a way. It might be cleaner work for you guys. Now, other things to keep in mind, this to the 0 is 1. I can ignore the 1s. I can ignore those ones. I can technically ignore those ones as well. But those are just things to keep in mind as you work this stuff out. So let's see. I got... And listen, there's no coefficient changes, so I'm just going to write up the answer straight up as is. So the final answer is a to the 9th, and I'll be bringing this down in a bit, plus 9 a to the 8th b squared. I forgot the b is squared. We still have to square these b's, if you know what I mean. Plus 36 a to the 7th b to the 4th, plus 84 a to the 6th b to the 6th. Why did I write a plus? It's a b. B is not a plus. B to the 6th. Now I'm going to bring this down because we don't need any of those top ones anymore, right? 9, 8, 7, 6. Notice B's aren't technically going by 1s. They're going up by 2s. 0, 2, 4, 6, 8, etc. All right, I need a to the 5th now. So here we go. Plus 126 a to the 5th, b to the 8th, plus 126 a to the 4th, b to the 10th, plus 84a cubed, b to the 12th, plus 36 a squared, b to the 14th, plus 9a b to the 16th, plus b to the 18th. Whew! Hoofa! Good thing they didn't have anything to multiply those coefficients by. Yeah, so that might have assisted me a little bit more. A lot of waste of space, but there it is. All right, we got 10 terms for this last one. I'm not looking forward to it because we do have a coefficient to multiply by. Y, and there are 2 variables for each of these as well. So y minus 3z to the 10th power. We just came off of 9. I'll probably do the same vertical thing as I did before. I'll split it up, though, in 2 different sets of columns, as long as it has some sort of organization. So n equals 10. Y minus 3z to the 10th. And again, you can do the same thing. You'll just have to pause it as the way that I get to do copy-paste jobs. But here we go. I got to write 9 again. It was 1, 9, and I can't remember what else. 26? 36. 36, 84, 126. And it's the same thing on the other side. I don't even know if it's worth writing, but 126, 84, 36, 9, and 1. Now 10 needs to be the addition of these numbers. So 1, 10, 45, 120, 210, 512, 250, wait, 252, 252. Is that right? I'm going to double check this one as well. 210, 120, 45, 10, and 1. Let's see where's... I still have that window open, but I did it for row 9. 110, 45, 120, 210, 252. Yep, okay. All right, there's row 10. So this time I kind of want to split it up into 2 different columns here. So I have y. This time I'll put the negative here, and then I'll clean them up afterward, because I do have some cleaning up to do on these. You know what I mean? All of these will need some... They'll need some cleaning up. So let's do this. We need 11 terms, though. So 1, 2, 3, 4, 5. I guess 6. And then 7, 8, 9, 10, 11. I liked it when it was an even number of terms, not an odd number. All right, my coefficients are 1, 10, 45, 120, 210, 252. That's the special one. And then it goes back 210, 120, 45, 10, and 1. Yeah, I feel like this is something I was doing at the time. And then this is to the 10th power, 9th, 8th, 7th, 6th, 5th, 4, 3, 2, 0. And then this is to the 0 and upward. All right, so hopefully this is making sense as far as Pascal's triangle, how this binomial expansion works. This is the absolute fastest way to do this. I'm not doing it slowly. I'm doing it with some speed stuff. I don't know, maybe my copying and pasting slowed me down, but it speeds me up at the same time. So pause that, write that down if you need to. I'm just moving these out of the way because I get little binder paper space. Why? Oh, it's an infinite cloner, that's why. Okay. All right, what I'm going to try and do now is write what they equal in here as well. I don't know how to shrink this, though, so this is the tough part. Okay, anything to 0 power is 1. Just get rid of those. Get rid of the ones there. We don't need them. All right, so this guy, I'm going to write him in green. So this is y to the 10th. This is, I'm going to do the best I can. 10 times negative 3 is negative 30. So negative 30, y to the 9th, z. 45 times negative 3 squared. 45 times 9 is 405. 405, y to the 8th, z squared. Now I have to do 120 times negative 27. So 120, I'm going to use my calculator. 120 times 27. Negative 3240. Y to the 7th, z cubed. And then 210 times, that's 3 to the 4th. 210 times 81. 17010. Yeah, you have a better way of doing this? Y to the 6th, z to the 4th. And then 252 times 243. That's 3 to the 5th, by the way. Negative 61236. Y to the 5th, z to the 5th. I have a little bit more room on that. My thumb. I'm getting these marks all over on my middle finger, my thumb, and all that kind of stuff. All right, next one's 210 times 3 to the 6th. These numbers are just going to get bigger, guys. 210 times 3 to the 6th. I think 729. So 153090. 153090. By the way, the final answer will be all these together. I wonder if it's worth like writing all together or just kind of what you see here. Z to the 6th. And then 120 times 3 to the 7th. It's going to be negative. 262440. 262440. Y cubed z to the 7th. And then 45 times 3 to the 8th. Maybe the numbers get smaller again. Nope. 295245. I bet the next time they'll get smaller. 295245. Y squared z to the 8th. 10 times 3 to the 9th. 3 to the 9th times 10 will add an extra 0. So 196830. Y z to the 9th. And then 3 to the 10th. 3 to the 10th is 59049. Z to the 10th. Okay, all those added together is your final result. This plus this, etc. I don't know if that's one of those things that maybe I can find a way to copy paste this in like a way that I don't have to rewrite them. Maybe I do. Okay, let's try that. I do have to write the final answer. I can't leave it separate. Go, hey, guys, figure it out for yourself. But you should. So we got y to the 10th minus 30y to the 9th z plus 405y to the 8th z squared. I hope I didn't mess anything up. Minus 3240y to the 7th z cubed plus 17010y to the 6th z to the 4th minus 61236y to the 5th z to the 5th. I want to see this on an answer key. Plus 15309y to the 4th z to the 6th minus 262440 y cubed z to the 7th plus 295. All right, there's your final answer, expanding all those. Okay, I'm gonna pause. I'll be back. Okay, I'm back. And yeah, you know, I was just thinking about how the initial problems were like, I'm gonna average a minute a problem, and this one was like, that was quite a bit. And I did the copy paste thing as well. Okay, yeah, that's not happening anymore. Okay, number 53. Finding a pattern. What is the sum of the numbers in each of rows 0 to 4 of Pascal's triangle? What is the sum? Oh yeah, this one's another one as well. This one's cool. I think this is the powers of 2, if I remember. So 53, I mean, I might have given it away. But let's just copy and paste it because the diagram will be helpful. Excuse me. Yeah, I think I spoiled it. But, okay, in row 0, so the sum here is, 1, and 1 plus 1 here is 2. And 1 plus 2 plus 1 is 4, 1 plus 3 is 8, 5, 11, 15, 16, 6, 16, 26, 31, 32. So, yeah, so you have these rows here. They said 0 through 4, but I got row 5. What is the sum of row n? Sum of row n. If you notice here, by the way, remember, row 0... that's also 2 to the 0 power. This is 2 to the 1st power, 2 squared. I forgot about this one. 2 cubed, 2 to the 4th, 2 to the 5th. So sum of row n is 2 to the nth. Okay? So another cool thing Pascal's triangle has. All right, 54. Finding a pattern. Describe the pattern. Oh, another one. Describe the pattern formed by the sums of the numbers along the diagonal segments of Pascal's triangle. What is the name? Oh, this is this one. What is the name of this sequence of numbers? Yaha. I mentioned this one. I didn't show you visually, but I said it out loud. I don't know if you heard me say it or if it was during the lecture or what. But again, Pascal's triangle, guys, it has a lot of things. These are just 2 of them. We already talked about combinations. Obviously, you build it from the building of these things. You see this here. You got 1. Let's see. I don't know where I'm going to write them, I guess, here. 1, 1, 2, 3, 5, 8. If you keep going. Wait, hold on. I don't think that's where the diagonal goes. The only there's an extra. There should be an extra 1 right there. It would be 13. I was like, what happened? Anyway, this sequence 1, 1, 2, 3, 5, 8, 13. I don't know if you know that one. This is called the Fibonacci sequence. The Fibonacci sequence is a sequence of numbers where the sum of the 2 previous numbers makes the next number. 1 plus 1 is 2. Hold on. 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 3 is 5. 3 plus 5 is 8. 5 plus 8 is 13. The next number would be 21 after that. Right? There are things, and just like Pascal's triangle, Fibonacci sequence is more than just that sequence of numbers. It does things. It's found in nature and different things with it math-wise that can be used. It's not just like, hey guys, I made a sequence, like that. All right, next exercises 55 and 62. Use the binomial theorem to write the binomial expansion. Okay, now let me check the lecture thing because this is where they used the combination things, but I forget if they actually. This says expand the binomial. I want to see if we actually. Give me a second. I want to go to it just because it's the lecture portion. It's a rough part of it. It was this part here. It says to write the expansion. Okay, they did still simplify it. Okay, I guess I'll write these numbers out. Depends on the problems. Okay. Anyway, we're still using what we were doing before. We are just using combinations. We're mentioning them as combinations now instead, though. So the problem is the numbers sometimes get a little big. All right, so number 55. So x plus 2 to the third power. You take 3, choose 0, and then you multiply by x. I mean, it's a lot of what we did before. Times x to the third times 2 to the 0. Plus 3, choose 1, times x squared times 2 to the first. Plus 3, choose 2, times x to the third times 2 to the... Oh, x to the third. I was looking at the one above. 3, choose 2 times x to the first times 2 squared. Plus 3, choose 3 times x to the 0, 2 cubed. So maybe this was where they wanted to hint more on this to the 0 power and stuff like that and use this formula that way. I might have prematurely used that part, but this is where combinations are hit. I'm not going to spend too long on the combinations aspects unless I don't know the numbers. But to find them in your calculator, if you're ever curious, in your calculator, you type 3 and hit math for the graphing calculator. Right here, go to probability and find the NCR. So 3, choose 0 would be here. And I can repeat those here. 3, choose 1. Second, enter. 3, choose 2. You're going to get 1, 3, 3, 1 for this. And 3, choose 3. There's also the formula as a whole, if you recall. That's the n factorial over r factorial times n minus r factorial, right? All that stuff. But there's the 1, 3, 3, 1 that gets involved. Anyway, I feel like I'm doing more on these problems than I need to. I probably will save myself time on these unless I don't know the binomial expansion. And I know the binomial expansion on all these ones. So I think this is just more practice of what we've been doing before, guys. But anyway, let me just write this extra step here. 1 times x to the third times 1 plus 3 times x squared times 2 plus 3 times x times 4 plus 1 times 8. So if that helps. So x cubed plus 6x squared plus 12x plus 8. And hey, if that's what you need to do for the problems, that's what you need to do, right? Sometimes the problems just need you to get them right. Okay, 56. I'm already kind of tapped out of using the combination stuff. I showed you how to do it in the calculator, but we've seen Pascal's triangle. In fact, I have it up above right there. And for those rows. Now, let me write out, actually, let me replace that with this one right here. I don't have row 6 on there, and it looks like I'll need it at some point, but I'll still use this one. So I'll use this, bring it down a little bit. I'll build row 6 when I need it. Coming up in a couple problems. We'll go from there. Hope that's okay. That first example was of what we were doing before, and this is still more of the same. So c minus 4 to the 5th power. We are using the binomial theorem. We are expanding binomials. So I start with 1 times c to the 5th. We're in row 5, by the way. This is row 5. 1 times c to the 5th. Change the sign. Minus 5 times c to the 4th times 4. Plus 10 times c to the 3rd times 4 squared. Minus 10 times c squared times 4 cubed. Plus 5 times c to the 1st times 4 to the 4th. Minus 1, or minus 4 to the 5th. Minus 4 to the 5th. Okay. So again, that would have been 5 choose 0 plus 5, or 5 choose 0, 5 choose 1, 5 choose 2, 5 choose 3, 5 choose 4, 5 choose 5. 5 choose 5 is 1, by the way. So this equals c to the 5th minus 20c to the 4th plus 160. That's 4 squared times 10. C cubed. 4 cubed is 64, so minus 640, c squared. 4 to the 4th is 256. 256 times 5. 1270. 256 times 5. 1270. 1280. Plus 1280. C minus 4 to the 5th. 1024. 4 to the 5th. 1024. Minus 1024. Okay. Yeah, you know, sorry if I'm not using the exact version of what they had and forcing stuff. I think that'd be a lot to write. Guys, you have to keep in mind here, I have 95 problems to do. And I'm only on 57. Honestly, this section is reminding me a lot of... Have you guys seen The Terminator? Row 4 here. Have you guys seen The Terminator where, you know, Kyle Reese is kind of trying to reveal to Sarah Connor, and he's like... gosh, how does that phrasing go? Where he says something like, it will not forgive, it... I don't know. I'd have to look it up. You can't like bargain with it. You can't reason with it. It won't show pity or remorse or something. And it absolutely will not stop ever until you are dead. And that's what I'm thinking what the problems are like. These problems do not show pity or remorse or anything. Anyway, 3b is the second term. This is to the first power. I'm using 14641 on this one. So 14641. And these a's are going down. And the 3b's are going up. One more. Plus 3b to the fourth power. Okay, so let's expand that guy. A to the fourth is the first guy. This is 12a cubed b. 12a cubed b. Okay, the next one. 3b, 3 squared is 9 times 6 is 54. So 54a squared b squared. 4 times 27 is 108. And then, I'm on my last term. And then 3 to the fourth is 81. All right. That was actually, I expected it to kind of get bigger. 58. Oh, 58 is going to have big numbers. All right. First of all, I have to expand to row 6 on this thing. So row 6 is going to look like it was 1, 6, 15, 20, 15. Whoops, not 20. 6 and 1. Or I could use 6, choose 0, 6, choose 1, 6, choose 2, and stuff like that. I mean, I know some of the numbers there, but that's row 6. It'll have 7 terms. We have a coefficient with a 4. And raised to the 6th power. Okay, so 4p minus q to the 6th. And yes, I'm going to stick with the way I'm doing it. I'm not going to go vertical anymore. So I got 4p to the 6th minus, changing signs, 6 times 4p to the 5th times q plus 15 times 4p to the 4th times q squared minus 20. 20 times 4p cubed times q cubed. And I'll tell you what, guys, the binomial theorem is important. I've been refraining from it because we have Pascal's triangle in here. It's important also when this is the same thing we use for binomial conditions and probability. If you did chapter 5 with me in IM2, it might have been section 5, 6 or something like that. We did something so similar looking to this. We didn't generally often expand these, but we would look at one at a time or a couple cumulatively. But you might know what I'm talking about with this. And if you do, good on you. If not, you can take a look at it. I think they're called binomial probability distribution functions, something like that. But there's more that you can look at with those. And these are used for this. These are used to come up with probabilities of certain things. What's the probability that someone with a 60% chance of hitting a target will hit the target 3 times out of 8 or whatever? Just all that stuff is actually involved. All right, so 6, 4p to the first, q to the fifth, and then plus q to the sixth. That's a 1. 1, da, da, da. Okay. 4 to the sixth. 4,096? 4 to the sixth. 4,096. Okay. So we got 4,096 p to the sixth minus 6 times 4 to the fifth. 6 times 1,024. I think that was that other number. 1,024. 6144. 6144 p to the fifth q plus 15 times 4p to the fourth. I think that's 15 times 2, 56. 3840. 3840 p to the fourth q squared minus 20 times 4 cubed. That should be 2080, right? 20 times 4 cubed. 1280. What did I say? Did I say 2080? I meant 1280. 1280 p cubed q cubed plus 15 times 16. Come on, 240. 240 p squared q to the fourth minus 24 p q to the fifth plus q to the sixth. Oh no. I gotta look at the Terminator line. I'm just gonna type Terminator will not stop. Whoa, what did I just do? Terminator will not stop quote popped up. The Terminator's out there. It can't be bargained with. It can't be reasoned with. It doesn't feel pity or remorse, or fear. And it absolutely will not stop ever until you are dead. Number 59 of 95. That's what the book reminds me of. W cubed minus 3 to the fourth. All right. W cubed to the fourth minus, this is 4, right? 14641. 4 times w cubed times 3 plus 6 times w cubed squared times 3 squared. From here on out, I should really just be squaring that number. Let's do that on the next problem. Minus 4 times w cubed to the first times 3 cubed plus 3 to the fourth. Okay. 4 choose 0, 4 choose 1, 4 choose... All right, this is w to the 12th minus 4 times 3 is 12. So 12w to the 9th. Remember, these multiply. Plus 6 times 9 is 54, w to the 6th. Minus 4 times 27 is 108. Minus 108, w cubed plus 3 to the fourth is 81. That actually wasn't as bad. Number 60. Oh, I just said it wasn't as bad. Now look at this one. 2s. It just gets worse. 2s. Oh no, it's s's. 2s to the fourth plus 5 to the fifth. They absolutely know when they this is probably the first section that I've griped about this for these things. These books, the Big Ideas Math books, absolutely are aware of putting s's with 5s as often as they can. I'm not joking. They absolutely are aware of what they're doing, and they said, hey. I don't know why they do, but they do. All right, row 5, 1, 5, 10, 10, 5, 1. Okay, so we got 2s. My neck. If you see me doing a lot of this and stuff like that, it's that time of the evening, guys. 2s to the fourth to the fifth plus 5, right? 1, 5. 5. 2s to the fourth. I'm going to put these 5s as they are. So 5 to the first power. So 1, 5, 10. And then 2s to the fourth cubed. And then 5 squared. And then 10. 2s to the fourth squared. Then 5 cubed. Then plus 5. 2s to the fourth to the first power. Then 5 to the fourth. Then plus 5 to the fifth. Okay. 2 to the 5th is 32. Oh, to the 4th to the 5th, so that's to the 20th. I got 5, so 25 times, 16, 400? 400 s to the 16th plus, I got 250, hold on, let's do 8, shoot. 8 times 25 is 200, times 10 is 2,000. I was trying to find the best way to do that multiplication. S to the 12th, that is an S, guys, that is an S. It's not 20,005. I'll put a little times there in case you're not sure. Plus 2 squared is 4. 4 times 125 is 500. Times 10 is 5,000. I hope I'm doing these ones right. S to the 8th plus 2 times 5 is 10. Times 6, 25, 6250. S to the 4th plus 3125. Okay, I put the little dots next to the S's to let you know which ones are S's versus that last one that's a 5 that got kind of cut off by the box. Okay, 2 more of these. Number 61. 3u plus v squared to the 6th. One, 6, 15, 20, 15, 6, and 1. All right, we're going to start with 3u to the 6th plus 6 times 3u to the 5th times v squared to the 1st plus 15 times 3u to the, oh, whoopsie, this 3u should be to the 5th on the outside. 15 times 3u to the 4th times v squared squared plus 20 times 3u cubed times v squared cubed plus 15 times 3u quantity squared times v squared to the 4th plus 6 times 3u to the 1st times v squared to the 5th plus v squared to the 6th. 1 times 3 to the 0 times v squared to the 6th. Okay, 3u to the 6th, 3 to the 6th, 304, 240, 729. 729 u to the 6th plus, okay, I have to work these out. 3 to the 5th is 243. 243 times 6, 1458. We probably had that number before. 1458. U to the 5th and v squared. I got 15 times 3 to the 4th, 15 times 81. 1215. We saw that number. Yeah, we saw some of these numbers before. 1215 times u to the 4th times v, that's a 4. Oh, that's a 4. I was trying to make it like a u. Times v to the 4th plus 20 times 27 is 540. 540? Shoot. Is that right? It's late. 20 times 27 is 54th is 0. 540. Okay. So plus 15 times 9. Why am I having trouble? 135. 135 u squared v to the 8th plus 18 u v to the 10th plus v to the 12th. All right, one more of these, and I know I'm probably doing these ones wrong in that I should be doing the Pascal's triangle thing, but I'm still getting the same answer. We're still doing these things. Now, this is to the 4th power. This is x cubed minus y squared to the 4th. Here's the great news about this, and I'm going to try and do this as mentally as possible. I'm going to try and do this mentally. 4th power is 14641, right? Those are the coefficients in these numbers. Now, remember, x cubed to the 4th is x to the 12th, so I'm going to start with x to the 12th. Minus. Now, I'm going to do x cubed, 4 x cubed cubed y squared to the 1st plus 6 x cubed squared y squared squared minus 4 x cubed to the 1st y squared to the 3rd. I mean, just look how the numbers go. I can confirm these are right in the end later. Plus y squared to the 4th. So x's go 12, 9, 6, 3, 0. Those go down by 3s. Y's go 0, 2, 4, 6, 8. They go up. You got 1, 4, 6, 4, 1, and change of sign. That's it. So I did skip steps. Sorry. All right. Let's go to numbers 63 to 70. Use the given value of n to find the coefficient of x to the n in the expansion of the binomial. So we're not expanding everything. We're finding a single term. We're finding a single term this time based on x to the n. All of these problems have x's in them. So we're trying to figure out when x is raised to the nth power based on what we see there, interestingly enough. Now we're finding out, so when n is 5, we want it to say x to the 5th power in that problem, in that part of the problem. So our original problem here says x minus 2 to the, x minus 2 to the 10th power. Now remember, these terms start with x to the 10th something, and then x to the 9th, x to the 8th, x to the 7th, x to the 6th, x to the 5th, right? These are different terms. Here's one term, another term, another. This term is where, these go down in order, whereas the negative 2's go up in order. This is negative 2 to the 0, 1, 2, 3, 4, 5. So this is negative 2 to the 5th there as well. Now, when we have x to the 5th is a result of, well, that thing being to the 5th power as well. We basically got to subtract that from 10. And then we find the coefficient. This is important that this thing's to the 5th power because in the combination realm of things, the coefficient that goes in front of here will be 10 choose and whatever this number is. These are going to be the same. 10 choose 5 because these go up. This goes 10 choose 0 when this is 0th power. 10 choose 1, this is the 1st power, etc. So I needed this to be 10 choose 5 to match for the 5th power there. I don't know if that makes sense, but we're finding this term here. We're going to use our calculator and do 10 choose 5 off of that, okay? So I go to the calculator and I do 10 choose 5. 10 choose 5. And I get 252. Now I got to multiply 252 by x to the 5th and by negative 32. Negative 32 times 252 is negative 8,064. So I get negative 8,064 x to the 5th as that term. They wanted the what? Just the coefficient. So the coefficient is negative 8,064. They wanted what value would come in there. Now that's just one term among them all, and that's the one we got. Now I don't know if it made sense on how I came up with these numbers here, but basically you got to look at what the second term is doing because, we got to match this one up. We got to get this variable to be what they want. They want this 5 to match up here. The fact that this was 5 was just coincidence right here, but this 5 matches with this 5 right here, and this 10 matches with this 10 right here. Basically, a lot of things got to match up with what we're doing there. I don't know if that makes sense, but that's what we're doing for all these things to work the way that we want it to. So let's try it again for number 64. On number 64, we have x minus 3 to the 7th power, where n equals 4. We want this thing to say an x to the 4th ultimately. But for x minus 3 to the 7th power, n equals 4, we need to get the term that will say x to the 4th on it. Now, when it says x to the 4th, it's also going to say negative 3 to the 3rd. It'll say to the 3rd because 4 plus 3 needs to add to 7. Now, we're going to be doing 7 choose 3 to make that happen because the 3 matches up here in the combination with the 3 in the exponent of the second term of the b value, that one. So we're going to do the same thing. I got to do 7 choose 3. I'll do it in the calculator now without you. 7 choose 3 is 35. So we get, and listen, I don't care about the x to the 4th so much anymore, but I'll still leave it. So 35 times x to the 4th times negative 3 cubed is negative 27. So we have to do 35 times negative 27. And we get negative 945. Negative 945 x to the 4th. Negative 945 is that coefficient. That is the answer that we're trying to get. Okay, number 65. X squared minus 3 to the 8th power, n equals 6. Does that mean we raise x to the 6th power? Because this x is already squared. Do I raise x to the 6th power to get x to the 12th, or do I raise x to the 3rd power to make it say x to the 6th? It says to find the coefficient of x to the n. I guess I do x to the 3rd. So with this one, I want to do x squared to the 3rd power. That's going to get me x to the 6th, right? That means I need my negative 3 to be raised to the 5th power, because 3 plus 5 is 8. And I'm going to be doing 8 choose 5 to get the coefficient that goes in front of there. So 8 choose 5, calculator, come here. 8 choose 5 is 56. We're going to be doing 56 times, there's my x to the 6th, times, and negative 3 to the 5th, negative 243. So 56 times negative 243. Negative 13,608. So negative 13608, x to the 6th. The coefficient is that one. Again, they're trying to find the one that matches for that x. That's the number. All right, number 66. 3x plus 2 to the 5th. Oh, my back. And n equals 3. So standard, we want the x cubed. So 3x is going to be cubed. Therefore, 2 is going to be squared. 3 plus 2 is 5. We got to do 5 choose 2. 5 choose 2. 5 choose 2 is here. 5 choose 0. 5 choose 1. 5 choose 2. That's 10. That's 10. 5 choose 2 is 10. I'm going to try this without a calculator. 10 times, this is 27x cubed times 4. So 10 times, let's see. Let's do 27 times 4 is 108. So 1080. 1080 cubed, I think. So 1080, I believe, is the number. So we get 1080 for that one. Again, just kind of a non-calculator version. Again, 5 choose 0, 1, 2, 3, 4, 5. If you have them on that table, you can figure them out. I won't know it for this next one, 67, where it's 12, because I don't know row 12 on this. That's where combinations are probably better than Pascal's triangle, unless you have Pascal's triangle handy, up to whatever number you want. Number 67, we're going to do 2x plus 5 to the 12th. That is a 10. To the 12th, where n equals 7. So we have to raise 2x to the 7th power. That'll raise 5 to the 5th power, and we're going to be doing 12 choose 5 to figure that out. So 12 choose 5 is 792. 2 to the 7th is 128. And 5 to the 5th is 3125. Oh, this is going to be a big number. So 792 times 128 times 3125 is, let me write it. 3168 followed by 5 zeros. 316,800,000. Oh, I still want to write that x to the 7th. That was the whole goal. But we have this coefficient. Okay, so good thing this isn't a whole binomial expansion, right? Number 68. 3x minus 1 to the 9th and n equals 2. It's not necessarily getting harder for questions. That last one is bigger, but n equals 2 might not be as big, especially with the negative 1. 3x is going to be squared, so negative 1 will be to the 7th, and we're going to be doing 9 choose 7 for that. 9 choose 7 I don't think is a big number either. What was it, 45? I can't remember. 9 choose 7. 36. Excuse me. That might have been for row 10. 36 times 3x, that's 9x squared. And negative 1. Negative 1 to the 7th is negative 1. 36 times 9 is 324. So negative 324 x squared. Much smaller number than the previous one. Feeling much better about that. All right. And then number 69, we have a 1/2 on this one. So 1/2 x minus 4 all to the 11th. And n equals 4 for that. So we have to do 1/2 x to the 4th power, negative 4 to the 7th power, and do 11 choose 7 on this guy there. So 11 choose 7. Who knows? Something big, I'm sure. Whoops, I did 11 choose 73. That would have been an error. Oh, 330, that's pretty big. So 330. Now, 1/2 to the 4th power is 1/16. This is 1/16 x to the 4th. Now, -4 to the 7th is also big, so that's also going to work itself against me. Once I was like, I'm going to divide by 16. Good, the numbers will get smaller. Well, nope, this is -16384. So we have to do 330 divided by 16 times 16384, and it's negative. We got negative, I guess it's kind of big, negative 337920, and that's x to the 4th power. So negative 337920. Let's put a comma there. And then the last one, number 70, another fraction. We have 1/4 x to the 6th, or x plus 6 to the 6th power, where n equals 3. Hopefully the number gets smaller again. That 6 is going to get something kind of big. All right, we're going to do 1/4 x cubed. 6 will also be cubed, and we're going to do 6 choose 3 in the process. 6 choose 3, here's 6 choose 1, or 6 choose 0, 6 choose 1, 6 choose 2, 6 choose 3, 20. So we're going to get 20 times 1/4 cubed is 1/64 times 6 cubed, oh, x cubed, oh no, let me fix that. 20 times 1/64 x cubed times 216. Let me get that for you. 20 times 216 divided by 64. Is it clean? 67.5, why not? Equals 67.5 x cubed. So 67.5 is yay coefficient. Yay. Okay, 25 questions to go. Number 71. Reasoning. Write the 8th row of Pascal's triangle as combinations and as numbers. Well, I'm close with, I did 8 at one point. I might copy and paste it. But as combinations would be 8 choose 0, 8 choose 1, 8 choose 2. There are going to be 9 of them. All the way to 8 choose 8. Whoa. There it is as combinations. You know what they want me to do is use the calculator. Now here's the thing. I could use it all the way up to one point, and remember on the other side it's symmetrically equivalent. Let's see if I did 8 choose 8 somewhere though. If I started to write it or something like that. There it is. I'm going to copy and paste that. Sorry, if I already did it, I'm not going to do it again. Sorry, not sorry. Gosh, I've done a lot of pages. Oh, I'm still not on that page yet. Not yet. I'll get there. All right, there we go. All right, that's number 71. Number 72. The first 4 triangular numbers are 1, 3, 6, and 10. Use Pascal's triangle to write the first 4 triangular numbers as combinations. Part A. Okay, hold on. 72. So 1, 3, 6, 10. You can do 1 as anything. You can do 0 choose 0 or anything. 3 is easy to do as 3 choose 1. 6 is easy to do as 6 choose 1. 10 is easy to do as 10 choose 1. Are there other versions that they're talking about? 1 choose, like 1. Is that all they want? Part B, use your result from part A to write an explicit rule for the nth triangular number. Oh, I see what they're saying. They mean the specific positions in Pascal's triangle. Got it. Okay, so the 1 on this one. Okay, I'm going to copy and paste this thing here. Sorry about that. It's like, what are you talking about? All right, yes, the triangular numbers do exist in Pascal's triangle. I didn't know they meant the specific. I didn't even see that. I was looking up top. I did not even see those. Okay, so this is row 0, this is row 1, this is row 2. So this is 2, choose 2. This is row 3, 3 choose 0, 1, 2. This is 3, choose 2. This is 4, choose 0, 1, 2. 4, choose 2, and I'm going to assume this is 5, choose 2. 5, choose 2. So use your result from part A to write an explicit rule for the nth triangular number t sub n. So if it helps, so this is the first triangular number. T sub 1, this is T sub 2, T sub 3, and T sub 4. What do we see as a pattern? First of all, the choose 2, and this number is 1 more than that number. So T sub n appears to be n plus 1 choose 2. You guys agree? N plus what? If T sub n, this is n plus 1 choose 2. They all seem to be the choose 2. So yes, this is part B. So part A is right there, and part B is right there. Okay, that makes a lot more sense as a problem. All right, numbers 73 to 76, use the binomial theorem to approximate the quantity to the nearest thousandth. For example, use the expansion 1.5, Okay, to the nearest thousandth is 3 decimal places. So let's use 73 to do 1.5 to the 6th power. I guess they started it off for us. So, it's 1 plus 0.5 to the 6th. So we're going to do 1 to the 6th. That's what they're showing by the 1. I'll just kind of write that. Plus, and the 6th is 1, 6, 15, 20. Where's Pascal's triangle? 1, 6, 15, 20, 15, 6, 1. All right, so we're going to do 1 plus 6. Okay, like they're not writing the ones either. Look at that. They're not writing 1 to the 5th or anything else. I'm not going to either. So 6 times 0.5 to the 1st power plus 15 times 0.5 squared plus 20 times 0.5 cubed plus 15 times 0.5 to the 4th plus 6 times 0.5 to the 5th. Remember, there are ones here that would be going down, but that's okay. Plus 1 times 0.5 to the 6th. Okay, and 1 to the 6th is just 1, right? So I'm just going to use the calculator for that straight up. It says use it to approximate stuff. I'm not going to write what the decimals are after the fact. I'm just going to type it in. You can watch me. So go to the calculator. We're going to do 1 plus 6 times 0.5 to the... Can I do this? No, I can't. This calculator doesn't let me hit the shift button and do anything with that. To the second, to the first. Oh, times 0.5 to the first. Oh, what happened? Hold on. 1 plus 6 times 0.5 to the first plus, I'll just have to click it, 15 times 0.5 to the second plus 20 times 0.5 to the third plus... Okay. It's approaching 11.391 to the nearest thousandth. So 11.391. And there we go for number 73. Okay. Number 74 to the 7th power. They're going to go 7, 8, and 9 on us, guys. They probably want us to use Pascal's triangle for these. How dare I, if so. Did I skip 7 as the Pascal's triangle thing? 1.95 to the 7th. Here's the thing. You can do 1 plus 0.95, or you can do 1 minus 0.05. Like that. I don't know which one's easier. The 1's still the same, right? I'm keeping 1 as it was. So 1. Now, these are going to alternate signs. Minus 7 times 0.05 to the first. Plus, I don't know the next one's on 7. I gotta use the calculator. 7 choose 2. 21. Plus 21 times, I just gotta remember them from 6, right? Times 0.05 squared. Minus, what were the other numbers? This was 6 plus 15, 15 plus 20. So 35, and then it'll be symmetry in a bit. 1, 2, 3, 4. Then there's symmetry the rest of the way. 0.05 cubed. So now plus 35 times 0.05 to the 4th minus 21 times 0.05 to the 5th plus 7 times 0.05 to the 6th minus 0.05 to the 7th. Okay. Honestly, it doesn't benefit anybody for me to for you to wait on me to do the calculation things. I'm gonna start typing this in. I'm gonna pause it. I'm gonna calculate it. I'll tell you what I get. Okay, and as I started to do the problem, I realized something really stupid. 1.95 is not 1 minus 0.05. It is 2 minus 0.05. So here's what I'm going to do. I'm going to turn this to a plus. I'm going to do 0.95. So I'm going to change all these to 0.95s, and then I'll go and recalculate it. My apologies to that. And these all have to be pluses now. So I started to calculate it, and I said, that number is very small. And let's go ahead and try that again. All right, let me pause it. All right, and I fixed this plus 2 right here, by the way. All right, so I got this answer here. 107.212 is what we want to round to there. 107.212. Yeah, you'll notice the first time I got this small number, 0.698 something. Yeah, 1.95 to the 7th is not going to be 0.695 something. So something clearly went wrong the first time. All right, so that is going to be that. That's all right, though. Let's move on to number 75. The numbers are just going to get bigger, so once I get to those values, I'm going to pause it again, things like that. Now, I think it's at this stage that I am going to use that the number above it, right? I just made a mistake last time. I was just trying to be fancy with it, and I screwed up. So 2.99 to the 8th power, I am going to do 3 minus 0.01 to the 8th power. There we go. So much better. Now, the only problem is 3 is going to have to be involved with all these. And in Pascal's triangle, we just saw those 8s. Where are they? Where are they? I need these numbers here. Give me them. I need them. I'm going to need 9 afterward. I know I built that somewhere. All right. So here's this guy. Okay. So this is going to be 3 to the 8th minus 8 times 3 to the 7th times 0.01 plus 28 times 3 to the 6th times 0.01 squared minus 56 times 3 to the 5th times 0.01 cubed plus 70 times 3 to the 4th. Whoa, that was a big eraser. Times 3 to the 4th times 0.01 to the 4th minus 56 times 3 cubed times 0.01 cubed. No, to the 5th. Keep looking at the wrong number. Plus 28 times 3 squared times 0.01 to the 6th minus 8 times 3 to the 1st times 0.01 to the 7th plus 0.01 to the 8th. Okay, let me use the calculator. Let me pause this thing. Give me a second. Okay, and after in a mass calculation here, I got 6388.068 when rounded to the nearest thousandth. 63, yeah. There's no reason you have to sit and watch me type that in. There are enough things that I've already written out that's like, should I just pause the whole video and just have you do it? I mean, I got to write it at some point, but there it is. Like this next one, right? We're going to do the 9th Pascal thing. I'm going to go and find that. I'm searching it from my list of things. Here it is. So we got to go to the 9th power. This thing is, once again, it's the Terminator thing, right? Can't be reasoned with or bargained with. It shows no pity or remorse or fear. And will not stop ever until you are dead. I'm not dead yet. Getting there. Getting there. Number 76. First of all, I'm going to put Pascal's triangle numbers up there. I just got to type even more. So 2.005 to the 9th power. That's 3 minus 0.995. Just kidding. It's 2 plus 0.005 to the 9th power, like that. All right, let's separate it. Here we go. We got 2 to the 9th plus, and they're all pluses this time, 9 times 2 to the 8th times 0.005 to the first. Sorry, I was thinking about things I could do in my calculator to make this easier, and I don't think I actually have anything. I was just thinking about it. Plus 36 times 2 to the 7th times 0.005 squared. What's going to mess me up on the calculator is accidentally missing one of the zeros. I can be certain of that. 84 times 2 to the 6th times 0.005 cubed plus 126 times 2 to the 5th times 0.005 to the 4th plus another 126 times 2 to the 4th times 0.005 to the 3rd. No, to the 5th. I'm going upward on these. They got to add to 9. Come on, Mr. Robinson. Plus 84 times 2 cubed times 0.005 to the 6th plus 36 times, remember, I got to type this in the calculator still, times 2 squared. Maybe you do too. You got to practice this as well. This isn't just mine. Oh, that's a 5 to the 7th plus 9 times 2 to the 1st times 0.005 to the 8th plus 0.005 to the 9th. Okay, all of them are pluses, which is nice. Give me a second. Let me type it. Okay, and with that one done, I'm getting 525.636 about right here. So 525.636. Okay. All right, guys, that is, I'm glad those ones are done. I feel like nothing was learned or gained with that stuff. There's no pattern recognition or anything for that one. So there's some problems that I have issues with. That's among them. All right, number 77, comparing methods. Find the product of the expression a squared plus 4b quantity squared times 3a squared minus b squared quantity squared using two different methods. Which method do you prefer, and explain? I mean, the only two methods I can really think of that they'd be talking about are either foiling these, full-on expansion, or using perfect square trinomials. I mean, no matter what, it's going to be what it is. But a squared plus 4, or they're talking about Pascal's triangle thing, right? I don't know. If they're talking about Pascal's triangle, we don't need to know it if we know our perfect square trinomial bits. So I'm going to do this. I'm going to make sure that the two versions that I do are unique. Okay. First of all, I got to copy the problem down right. I'm having trouble writing now. Okay. So first thing I'm going to do is binomial expansion. So, perfect square trinomials, and then kind of foil them out. So first one is going to be you square the first term, plus you double the product of these two, plus you square the last term. Okay. On the next one, you square the first term, minus you double the product of these two, plus you square the last term. Okay. Pretty straightforward so far. Now we multiply these ones out through just multiplication. So 9a to the 8th minus 6a to the 6th b squared. I'm doing a to the 4th times these. Plus a to the 4th b to the 4th. Now I'm going to do 8a squared b squared times these. Plus 8a to the 6th. No, not 8. 72. Plus 72 a to the 6th b squared. Minus 48 a to the 4th b to the 4th plus 8a squared b to the 6th. And then the last set, plus 16 times 9 is 144, plus 144 a to the 4th b to the 4th minus 16 times 96 a squared b to the 6th. Oh yeah, we have one of those. And then plus 16b to the 8th. Some of these look like they do combine. So, and I'm not going to try standard form. Well, they are standard form, sort of. But 9a to the 8th. Let's get the a to the 6's now. Negative, let me cross some things out. Negative 6a, so the a to the 6 b to the 6. So I got one right here, here, and that's it. So that's 66 a to the 6th b squared. So get those out. Let's go to a to the 4th b to the 4th. I got 3 of them. I got 1 a to the 4th b to the 4th minus 48 plus 144. So 145 minus 48 is 97, I think. This is where I might make a mistake here somewhere. I don't know. And then a squared b to the 6th is negative 88 for those two. And then plus 16 b to the 8th. I got to move that over a little bit. Plus 16 b to the 8th. So that's one method. That's the faster of the methods in my book. Now, there's another one that I want to do that actually this other method might be just as fast if I kind of know what I'm doing with it. You'll see what I mean when I get there now that I just realized it. I think it's going to work kind of well. Now, I don't want to use Pascal's triangle for any of these things, right? I'm using binomial expansion of perfect squares. I hope that's okay. Let me take this original problem again and show you what I want to do this time. This time, I want to multiply these things separately here, like do, let's see how I say it. I want to do this times, shoot. I'm trying to copy and paste it and write it all as once. Okay. I want to do these things separated and expanded. So this times this plus this times this kind of thing. So it's like a squared plus 4b, or a squared plus 4b squared times this plus, shoot, I can't move that parenthesis. This is hard to do. Excuse me. I need to condense this more. I don't know if this is what they mean. If they probably mean Pascal's triangle, guys, I'm not using Pascal's triangle. Oh, well, I'll leave that there. I'll just condense the next one. Times another set of these. A squared plus 4b squared. Now, it's going to kind of look the same. Actually, I don't know if it will. 3a squared minus b squared. So basically, I'm going to multiply these two and then multiply these two. Now, multiplying one of them will give me the same thing twice. This actually might go quicker. Oh, no, it won't. Anyway, it won't go quicker. But okay, anyway, I'm just going to do that. So FOIL this thing out. I get 3a to the fourth minus a squared b squared plus 12a squared b squared minus 4b to the fourth. Now, keep in mind, this thing's going to be squared whatever we do. So I'm foiling within and then squaring the result. So that's going to be 3a to the fourth plus 11a squared b squared minus 4b to the fourth. So it's two of those. I was going to say if I square it, it would be faster. The problem is this is a trinomial squared, and we don't have a special product property thing for that. So I thought it was going to be a binomial squared. I don't know why. I just thought that was the case. So I got to do two of these. 3a to the fourth plus 11a squared b squared minus 4b squared. There's no, or minus 4b to the fourth. There's no trick to know this as far as I'm concerned. There's no trick. We just got to multiply it out however it is. And we should get the same answer. Let's start with 3a to the fourth multiplying by these. So 3 to the fourth times 3 to the fourth is 9a to the eighth. And then plus, we got 33a to the sixth b squared minus 12a to the fourth b to the fourth. Then I got to do 11. See, I'll try and line these up. 11a squared p plus 3a to the fourth, that's 33 again. 33a to the sixth b squared plus 121a to the fourth b to the fourth. And then I have this guy. This one's actually kind of cooler. Minus 44a squared b to the sixth. And then minus 4b to the fourth. 3a squared minus 12a to the fourth b to the fourth. Negative 4b to the fourth. This is minus another 44a squared b to the sixth. And then plus 16b to the eighth. Kind of like this one. A little bit more how they line up and do certain things. Let's see. 9a to the 8th doesn't combine with anything. This one was 66a to the 12th. No. Oh, shoot. No. Those don't combine. I forgot what I was looking at. This is addition. 66a to the 6th b squared. Negative 24. That's 97. A to the 4th b to the 4th. This doubles up as negative 88 a squared b to the 6th. And this is 16b to the 8th. Now, do I have the same answer here? 9 8 8, 66, 97, 8 of 88, 16. 9 8 8, 66, 97, 8 of 88. Yes, I do. Same answer. So, question is, which one do I like more? I think this one had less steps. I think this one had less rhyme and reason in its pattern at the end, but this one had less steps for me overall to do. So, I preferred my method number one. Because it required less steps. Method number two had great patterns, addition patterns, however. Now, both of them, one of them was kind of like foiling first, or like combining the two different things first and then squaring second, but the squaring didn't have a pattern. So I don't know. I guess it depends on what the numbers are. All right, that's number 77. Let's go to number 78 on thought-provoking. Now, by the way, 77, I bet that they had different methods in mind. I thought they were Pascal's triangle. I'm not going to prefer Pascal's triangle if I know my perfect square trinomial thing. So if that's what they were talking about, I'm not even dealing with that anyway. Adjoin one or more polygons to the rectangle to form a single new polygon whose perimeter is double that of the rectangle. Find the perimeter of the new polygon. Well, the rectangle... What? The rectangle... Let me just draw a rectangle. Let me do the rectangle shape. The rectangle has 2x plus 3 and x plus 1. Its perimeter is doubling the x plus 1s, doubling the 2x plus 3s, and adding to... What does this have to do with what we're working on? Oh, I guess this is the addition things. I was thinking about the Pascal's triangle stuff. 2x plus 2. I forgot this was the same section. It's been a while. Perimeter is 6x plus 8. Now, they said adjoin one or more polygons to the rectangle to form a single new polygon whose perimeter is double that of the rectangle. So it's a brand new shape that makes the thing. So, okay. So, double the perimeter is 12x plus 16. So, I need to get this perimeter with this thing if I adjoin something to it. Thought-provoking is always open-ended, and this is like, say, be creative with what you got. So let me copy-paste this. Now, if I adjoin something to it, that means I'm going to lose one of the shapes in it. Okay, for some reason, these can't move. I'll lose one of the sides, basically, if I adjoin something. It says one or more. I'll try and adjoin one of them to it. Let's keep, say, the 2x plus 3s here. Let's keep that x plus 1. So far, these ones in total have 4x, 5x plus 3, 6, 7. 5x plus 7. I still need a remaining, for whatever shape this is going to be, I still need a remaining 7x plus 9 with all of these combined. So for 7x plus 9, it doesn't need to be a regular polygon or anything, right? Whoa. Those did not need to be together. So for 7x plus 9 on this, we could make like a... I want to keep that shape intact. Let's do like 1, 2, 3. I don't know. We can make anything up, right? Whose perimeter is double that of the rectangle. Do we want to do something dandy with it? Let's see. I'll at least make decent looking shapes. Let's do 1, 2, 3, and 4. And it's not going to be quite regular. I mean, it kind of looks regular. 7x plus 9. Let's see. If I do... Oh, what happened? If I do... Okay, these won't be perfect, though, right? Should I make them perfect, Ask? 7x plus 9. How about this? If these were 1/2 x's, 1/2 x, 1/2 x, and then these were therefore 3x's, 3x plus 3x is 6, I said it as 7x. Now I need 9 to come into form. Let's make these 3. Now, I'm getting boring with my numbers. Instead of 1/2 x, I write 0.5. 0.5x. I'm getting too cute with this. 0.5x. 0.5x. Let's do... I'm trying to make it all congruent looking. Plus 1.5, 1.5. That's 3 and 3. And I need these to be 3 and 3. Okay. I think that gives me a new shape with 12x plus 16, which is double the perimeter of the original. The original would have been 4x plus 6 plus 2x plus 2, which is 6x plus 8. Double 6x plus 8 is 12x plus 16. This is 3, 6, 7, 8, 9, 10, 11, 12x plus 3, 6, 9, 15, 16. 12x plus 16. Okay, so that's good. The perimeter of the new shape now, keep in mind this would have been x plus 1. So perimeter of new shape is going to be, when they, or of the new polygon. The new polygon is 7x plus 9, right? So 7x plus 9 plus x plus 1, which is 10x plus 10. Now, I don't know if all polygons want to be 10x plus 10 with that. No, because it depends on which thing you enclose off. But there's mine. They said do more than one polygon if you want to. I just did one. Okay. It's kind of tricky because I tried to be tricky with it. Numbers 79 and 80, we got some solids. In exercises 79 and 80, write an expression for the volume of the figure as a polynomial in standard form. Okay, got it. So 79, we have a rectangular prism where the volume is, they tell you, length times width times height. I wonder why they're being so helpful when we should know what they are. I don't know. All right, I'm going to do one at a time. We'll do x plus 1, or two at a time. X plus 1 times x plus 3, which is x squared plus 4x plus 3. We'll now expand that to 2x is going to multiply by these, 2x cubed plus 8x squared plus 6x plus 2x squared plus 8x plus 6, which gives me 2x cubed plus 10x squared plus 14x plus 6. This is in whatever cubic units. They don't actually have any units for this. How long have we gone? Oh, pretty long. Number 80. The real question is, will I have enough room on my thing to get this all done? I think I have to work a little bit faster, guys. Number 80. Volume is pi r squared times height. Okay, your radius is x minus 2. Your height is 3x minus 4 of the cylinder. All right, volume is pi times x minus 2 squared times 3x minus 4. Now, it needs to be in standard form. That means pi is going to multiply by everything in the end. I'm going to write 3x minus 4 first because I'm going to do x minus 2 squared here. X squared minus 4x plus 4. So 3x times x squared. 3x times negative 4x. Whoopsie. That's what happens when you speak as you write. Negative 4x plus 12x. And then negative 4 times these. Negative 4x squared plus 16x minus 16. All right, pi is going to go into every single term here, okay? So I'm going to get 3 pi x cubed x squared minus 16 pi x squared. 12x plus 16x is 28x plus 28 pi x, and then minus 16 pi. So there's your standard form of that guy. I think they might not have to do pi on the inside there on those. I don't know. For standard form, maybe, maybe not. I'm being safe. Number 81. 2 people make 3 deposits into their bank accounts earning the same simple interest rate R. Why does the money go down? Oh, it's how much they deposited. Okay. Persons A, oh, they have models down here. Person A's account is worth this on January 1st, 2015. Write a polynomial for the value of person B's account on January 1st, 2015. So let's just use their same numbers, 2,000, 3,000, 1,000. So person B will be 5,000 times 1 plus r quantity cubed plus 1,000 times 1 plus r quantity squared plus 4,000 times 1 plus r. Write the total value of the 2 accounts as a polynomial in standard form. Then interpret the coefficients of the polynomial. So what we have to do... Okay, let's do this on the side. Now, they said standard form anyway. Remember, 1 plus r is also r plus 1. R plus 1 quantity cubed, guys, is r cubed plus 3r squared plus 3r plus 1. And r plus 1 squared is r squared plus 2r plus 1. And of course, r plus 1 is r plus 1. So keep in mind when we do those, okay? So account A, we're going to do 2,000 times this plus 3,000 times this plus 1,000 times this. And account B is going to be doing those same numbers, or sorry, different numbers, but those same variable things. Now here's the thing. I can combine like terms before I distribute. So actually, let me do this. A plus B, sorry, I'm saving space and time. A plus B, I can add 2,000 on A with 5,000 on B to get 7,000. Okay, I can actually add those up before I distribute into there, so I don't have to do it twice. So 7,000. And then 1,000 on B plus 3,000 on A is 4,000 for the second set. 4,000. And then 1,000 plus the 4,000 on B is 5,000. Now I can distribute. So this will be 7,000 r cubed plus 21,000 r squared plus 21,000 r plus 7,000. I hope you can see that here, 21,000. Plus I got 4,000 r squared plus 8,000 r plus 4,000, and then plus 5,000 r plus 5,000. All right, they combine to become 7,000 r cubed plus 25,000 r squared plus 34,000 r plus 16,000. Like that. So there's the combination of all them boys, A and B, combined in standard form. Interpret the coefficients of the polynomial. I don't even know how this interest thing works. Person's A's, oh, the r cubed. I just don't know how the cubed stuff works and all that, but I don't know. Is it that the 7,000 is how much money is gained? Oh, to the third power is how many times you do it that many times, because they do it. I got it, because they deposit it then and it builds up over that time. So 7,000 is the amount they gained in total, right? Is the total, I should say, total amount they gained in interest. Wait, it's not that they gained interest because they deposited. It's the total amount of money that gained interest for 3 years, because that r cubed. 25,000 is for 2 years. Now that makes sense. I was confused on the interest thing for a second because I don't see an actual r value. 34,000 is for 1 year. One year's, and 16,000 is how much money's invested without any interest. Money invested. Okay, there we go. Part C. Suppose their interest rate is 0.05. What is the total value of the two accounts on January 1st, 2015? Okay. R is 0.05. That's 5%, by the way. So we're just substituting now. We get to do all that. So 7,000 r cubed. I'm typing this in the calculator. 7,000. I'm going to put x cubed. Sorry that you can't see this. I'm just typing. Plus, where is it? Plus 25,000 x squared plus 34,000 x plus 16,000. Now I'm going to type in 0.05 for r. So 0.05, and I'm getting 17,763. 17,763.375. I'll say 0.38. Rounded to the nearest cent. So that's the total amount for those two together. If I round up, I don't know if they get to round up for you when it comes to money, but there it is. All right, let me see how much room I have left here. I got 3 out. Let's see. I have, my computer runs short on room at sometimes. I'm really pushing my time here. That's really why I have some bits where I feel like I'm rushing now, because I got to get to problem 95 and done before I'm out of here. These problems look like they're bigger. Like, look at all these. These are kind of big. Complete the table. What characteristic of Pascal's triangle does the table illustrate? I don't know yet. All right. 3 choose 1 I know is 3. I wish I knew some of these. 5 choose 2. Let's see. 1, 5. Oh, I don't remember. I'm going to pull up Pascal's triangle, guys. Unfortunately, I don't have time for like guessing or building or something like that. Okay, I'm going to put in a massive one in here in case it's needed. Actually, what do we need up to? 12? How about this one? This one goes up to 13. I'm going to copy and paste this for a second. I want you to take a look at this. There we go. All right, I'll keep this as reference down in the bottom. This 3 choose 1 is 3. 5 choose 2. Here's 5 choose 0, 1, 2 is 10. 7 choose 4. 0, 1, 2, 3, 4 is 35. 8 choose 3. 0, 1, 2, 3 is 56. 10 choose 6. 0, 1, 2, 3, 4, 5, 6, 210. And 12 choose 8 is 0, 1, 2, 3, 4, 5, 6, 7, 8, 495. N choose N minus R. Won't these be symmetrical? N choose N minus R is like 3 choose 3 minus 2 is 2. And this would be like 5 choose 3. These should be symmetrical. 7 choose 3. Let's just try those ones and make sure they work. 3 choose 2 is 3 choose 0, 1, 2 is 3. 5 choose 3 is 5 choose 0. Oh, wait. 0, 1, 2, 3. 7 choose 3 is 7 choose 0, 1, 2, 3. Yeah, these are going to be the same. 56, 210, 495. There's symmetry in Pascal's triangle. That's the basic gist behind it. All right, so that's filling out the table. Now, what were their questions? What characteristics of Pascal's triangle does the table illustrate? Oh, symmetry. That was kind of dumb. Sorry. There is symmetry in Pascal's triangle. I don't know. That's all I'm going to say. We've seen that a whole bunch. You can look at it right here. Clearly, there's symmetry there. Okay. Let's keep moving forward. Number 83. Binomial experiment. You roll a 12-sided die. Oh, yeah, this is the probability stuff I was talking about before. This is where they're used. You roll a 12-sided die 8 times. Let P be the probability of rolling a multiple of 3. Let Q be the probability of rolling a number that is not a multiple of 3. The probability of rolling a multiple of 3 exactly K times in N rolls is this. Expand that. No. I don't want to expand it. Okay, I might have to do it on pause here. But it says expand this using the binomial theorem. So 2/3 plus 1/3 to the 8th power. Now, the interesting part is they said a multiple of 3. What are multiples? Oh, it's a 12-sided die. That's why. No, it still doesn't make sense. What are the multiples of 3 on a 12-sided die? 3, 6, 9, 12. What are the ones that are not a multiple of 3? Everything else. So 2/3 should be the second thing? I don't know. Anyway. Okay. As far as expanding this is going to be... Sorry, I got to use Pascal's triangle for this. I might have to write this out. Let me pause it. All right, so the first thing I did was I copied over Pascal's triangle here. Remember, they use the combination thing. What they say for n choose k is like 8 choose 0, which is 1. 8 choose 1, which is 8. 8 choose 2, which is 28. So I'm putting those in here straight up. I got to write the expansion. They said expand using the theorem. Interpret each term in the context of the problem. Now, I'll tell you what it is in a moment, but I don't know if they really want me to actually get the fractions, because otherwise these are rounded decimals. So I think I'm going to write them as fractions. So let me pause that and do that same thing. Okay, so this is what I got from these ones here. If I did decimals, it would have been terrible. Now, the cool thing is these all divide by 6,561, because that's 3 to the 8th power, I guess. None of the numbers on top will ever reduce with the fractions there. Now, these numbers represent probabilities. Here's the big part that this also with binomial things. The thing that only confuses me is that they put the 2/3 first. When they said the thing, they said you roll a 12-sided die 8 times. Let P be the probability of rolling a multiple of 3. Now, you get a 1/3 probability of rolling a multiple of 3. I want to make sure you guys know that. 3, 6, 9, and 12 are the multiples of 3. 1 and 2, 4 and 5, 7 and 8, 10 and 11 are the non-multiples of 3. So these are the probability of not doing it versus probability of yes doing it. It says, let Q be the probability it's not a multiple of 3. That's the 2/3. The probability multiple exactly 3 exactly K times an n rolls. So what this says here is the probability that you'll roll. Let's see how I say it. You get 8 rolls. These are the probabilities of rolling a multiple of 3 this many times. So these are the probabilities you'll roll a multiple of 3 exactly either this is the first one is 2/3, right? So this one is, oh shoot, hold on, let's see, maybe it's backwards now. If 2/3 is to the 0, that's why they have it backwards. Got it. So this is 0 times, because that 1/3 is to the 0, is to the 0 power then, and this is 1 time, 2 times, 3 times, etc. 4 times, 5 times, 6 times, 7 times, and all 8 times. There we go. Okay, that's why they have it backwards like that, because I forgot the second terms to the 0 power. That's why it's going like that. Anyway, you get a 1 out of 6,561 chance of rolling a multiple of 3 all 8 times. Very slim. All these are relatively slim. Some of them, obviously, this builds up to 100%. If you add all these probabilities, it's 100% because one of them has to be hit for that number of multiples of 3. So that's the question. So they expanded on what they were talking about with it as a whole. Okay, number 84 on problem solving. The sphere is centered in the cube. Find an expression for the volume of the cube outside the sphere. So I guess we got to subtract this cube's, the sphere's volume. What's the 3? Oh, 3 is this width. 3 is the width that's right there like that, and they call this thing a cube. Let's talk about the sphere first. So the volume of the sphere, the radius is x plus 2. So that's 4/3 pi r cubed, which is going to be 4/3 pi times x cubed plus, now we got to do 3 times x squared times 2 plus 3 times x times 2 squared plus 2 cubed. That's the expansion of that cube. So x cubed plus 6x squared plus 12x plus 8. Leave it like that for now, I guess. I don't know. We'll leave it like that for now. Now, the cube has a length there of 3. Another length on there would be 3 if it's centered inside there. So 3 and 3 is 6. That means that this entire length, x plus 2 and x plus 2. So the entire cube length, cube edge length is 2x plus 2's plus 2 3's. So it's 2x plus 4 plus 6, which is 2x plus 10. So the cube's volume of the cube is going to be, oh, that's right, you get to cube this thing, is 2x plus 10 quantity cubed. How about I do this? I factor, oh, wait, that doesn't work that way. 2x plus 10 quantity cubed. You know, I could factor the 2 out. Let's see. It's 8 times x plus 5 quantity cubed. It's basically this. You get to do 2 factored out of there, but it's still inside the cubed. And then you cube the 2 and you get 8. So 8 times x plus 5 quantity cubed. So I'd rather do that. 8 times x cubed plus, we'll do 5 times 3. 3 times 5 is 15 times x squared plus 3 times 5 squared is 3 times 5 squared is 25. So 75x plus 5 cubed is 125, which is 8x cubed plus 15 times 8, 120. 120x squared plus 8 times 75, 600. X plus 8 times 25 is not 200. 1,000. 1,000. Okay, we have to do the volume of that guy minus the volume of that guy there. Now, I have to distribute that 4/3. Find an expression for the volume of the cube outside the sphere. I have to distribute that 4/3. So that'll be 4/3 pi x cubed. Well, I can't combine like terms anyway because he's a pi in it. So maybe I keep them separate. Maybe just keep them separate. I'm trying to think if that's allowed because they have, I don't know. 4/3 pi x cubed plus 4/3 of 6 is 8. So 8 pi x squared plus 4/3 of 12 is 16. 16, I'm definitely fretting over time here. And 4/3 of 8, that's 32/3 pi. Okay, so my volume of my total equals, so I can do 8 minus 4/3 pi x cubed. I'm going to keep them all as like separate thingies here. I'm doing this minus that. Plus 120 minus 8 pi x squared plus 600 minus 16 pi x plus 1,000 minus 32/3 pi. I don't have, I mean, there are other ways I could write it. I don't know if they want them combined in terms of that or not. When I say they, it's like whatever. You just got to do one thing minus the other, and that's the way that I'm going about it. So I don't really know what a best way is, but that's, I guess that's just kind of my way. I don't want to do a rounding. I'm not going to round. It didn't say what to do there. I don't want to round. I'm going to leave it like that. If you do, though, for example, if you do 8 minus 4/3 pi, like I get 8 minus 4/3 pi, I can round that number to about 3.8-ish, whatever. So that's what I'd be working on. I'd have 3.8x cubed something, something, something. But that's what I'm working off as exact numbers, and you can round that as needed. Okay, let's go to number 85. Making an argument. Let's see if your friend's right again. Your friend claims the sum of two binomials is always a binomial, and the product of two binomials is always a trinomial. Is your friend correct? Explain your reasoning. Heck no. Come on, friend. 85. No. Do a binomial. Here, let's do x plus 3 plus x squared plus 7. Is this? That's x squared plus 3. Whoops. That's x squared plus x plus 10. Trinomial. No, the sum of two binomials isn't always a binomial. The product of two binomials is always a trinomial? No. X minus 9 times x plus 9. The product of two, that's x squared minus 81. Binomial. Come on, friend. I'm moving on. Number 86. How do you see it? You make a tin box by cutting, oh, we've done this kind of stuff before, by cutting x inch by x inch pieces off of tin off of the covers of a rectangle and folding up each side. I don't know if you can imagine what that looks like, but the x's now come up because the corners are gone. They can like line up together now, basically like that. The plan for your box is shown. Okay. What are the dimensions of the original piece of tin? And write a function that represents the volume of the box without multiplying determinant's degree. Okay. So it sounds like the volume one, you don't actually have to do the actual write in standard form thing. But on 86, let's copy paste that guy. This is of 10 problems I still have left to do. I'm still wary on time here. Let me do myself a little time. I only can look at my gigabytes on my computer, and I don't know what it represents as a whole. So I don't know. How deep am I into this? Pretty deep. That 3.5 hour thing, Lumen. Okay. So part A, says, what are the original dimensions? These x's get added to these. So 12, this is 12 minus 2x plus the 2x's, which means those go away. And this is 6 minus 2x plus the 2x's on top and bottom. Those go away. So the original dimensions of this box were 12 by 6 inches. Dimension equals 12 inches by 6 inches. Then we cut x inches into them. B, write a function that represents the volume of the box. So now on B, your volume is going to take that 12 minus 2x, the length, times width, 6 minus 2x, times the height of x, like that. It says without multiplying determine its degree. So this is it, by the way, in cubic inches. They said don't multiply. It's not really, this isn't a hard one to multiply, but this would be an x cubed. It would be a cubic. Because eventually at some point, this multiplies with this, multiplies with this. X times negative 2x times negative 2x is positive 4x cubed. That'll be the leading term. Anyway, that's as much as we're supposed to do there. Apparently, it says without multiplying. So that's how we see it. Number 87 to 90, using tools. Use a graphing calculator to make a conjecture about whether the two functions are equivalent. Explain your reasoning. Well, the reasoning for each and every one of these will be if they get the same graph or not. So here's what I'm going to do. I'm going to pause each time I type a new function, then I'll reveal what the graphs look like. All right? Give me a second. All right, guys, I'll do you one better even on these. So here's what I did. I'll show you in the graphing calculator. So in y equals, I actually created all the equations already, all of 87 through 90. Now, on 87, it's these two equations right here, y1 and y2. On the next two, y3 and y4, it's number 88, and y5 and y6 is number 89, and y7 and y8 is number 90. Now, some things you can do feature-wise is this. See where these equal things are highlighted? That means these ones will actually be graphed. You hit the enter button to cycle through if you want to highlight it or not. If I press enter, it's no longer highlighted. It'll no longer be graphed. If I press enter, it will. So you can see that my y3 and y4 are not going to be graphed right now. I'm going to leave them. It was like this before, and I disabled it. The other thing I'm going to do is this, and it's these things on the side. I don't know if you noticed. This is the default line thing. It's just a normal thickness, and I made it this version for the next one. You hit enter to cycle through the different things that it can do here. So I have one in normal, and I have the next one in bold. And you know, as it traces over, one's going to start tracing. If the other traces exactly through it, I can tell it's the exact same graph. Now I have the normal, the window normal, negative 10 to 10. We'll see if that's going to be enough. But my basic thing is, do they go in the same path? And if they do, I'm going to say they're the same graph. I hope I can see them on them. We might not be able to, depending on how deep they are. Let's zoom out a little bit. Let's go negative 20 to 20. Let's just make sure that we hit the points. Maybe these graphs are so sharp that we don't need... Actually, let's keep the x's small. Let's keep the x's small. I think the y's need to be taller because these are like bigger polynomial graphs. So let's see what this looks like. I'll hit the graph button. Let's see if this works. This is for 87. So there's one of them. And there's the second one. They look like the same graph to me. I'm going to assume that they are based off that. That's my conjecture. That's not guaranteed, but they look the same. So 87 remembers the same, okay? We're going to do all these together. Number 88, let's hide these ones away. And let's get these ones here. Number 88's the next two. Okay? Let's look at these two graphs. Here's the first one. There's the second one. So those are different, right? Unless I type the equation wrong, those are different graphs. So same on 87, different on 88. Remember that. I hope these are typed correctly. Okay, let's say x plus 2 to the 5th, x to the 5th. I'm going to assume they're typed correctly. Number 89. Boom. And boom. All right, number 89. Ooh, those look slightly different. Hold on. What were those the same path? Let me zoom out more. I couldn't tell what the rest of that graph was doing. Were those different? Let's just go farther out. Negative 40 and 40. Oh, whoa. I want 40, not 4. I couldn't tell if that one went lower or not. Shoot, I'll hit the other part of that graph. It looks like that's going lower, doesn't it? Let's look in the table. I couldn't tell on that one. They said use the graphing calculator to make a conjecture, but oh, those are slightly different. Oh wait, hold on. Those are slightly different. These are the equations. That's y5 and y6. One is one more than the other. That is mean. Did I type these right? Plus 80. Oh, that's supposed to say a plus 81. No, I typed it right. But the equations, if you take a look, this one says plus 80. If that said 81, they'd be the same. But it's one less. That one's pretty rude. That one's different. Just barely. That one's one off. Now I don't know if the other ones were on or off. I'm going to pretend like the other ones were as they appeared. So anyway, those are my conjectures so far. So same, different, different. And then the last one, I hope I'm not too zoomed out for this last one here. Because that was a quartic, right? So the cubic, we should be able to see a bunch of these too. Let's see if they're the same or not. Last one. There's that. All right, I'm going to guess those are the same. Let's look at the table. Yeah, those are the same. So I should have looked at the tables before. So same, different, different, same, right? So that's me answering all four together. I hope that's okay. So 87, same. I'm not going to write them. 88, different. 89, different, which that one looks barely different. You had to be careful. That one, I see someone could mistake it as the same. I understand. Now, it says use the graphing calculator to make the conjecture. My whole thing on 88 or 89 was them being different was because I should be raising... Why did I say this should be an 81? Because at some point you got to do 3 to the 4th power or negative 3 to the 4th power. That would give you an 81 instead of 80. I don't know how the graphing calculator has to do with making that conjecture other than looking at the equations to do that. But hopefully there's no... I mean, if the equations are different, then they're different, right? Anyway, here we go. 91, rewriting expressions. Expand the complex number 1 plus I to the 5th and 3 minus I to the 6th. Simplify your results using the fact that I is defined as I equals square root of negative 1. So on A, we have 1 plus I to the 5th power. Okay? Now 1 plus I to the 5th, we have to expand that. Is it 1, 5? I forgot my numbers. Where's my Pascal's triangle I last used? There it is. 1, 5, 10, 10, 5, 1. I should know that one. All right, 1, 5, 10. So this is 1. So the cool thing is ones are just ones, right? 1, 5. This will be I. 10. I squared. Let's see. I don't even need parentheses. 1, 5, 10. 10, 5, 1. Okay. Now, 5i is exactly that. 10i squared. If I is square root of negative 1, then I squared is negative 1. I cubed would be negative 1 times I, which is negative I, and I to the 4th would be 1, and then it should repeat itself after that. So I'm going to leave the 5i there. 10i squared is negative 10. 10i cubed is negative 10i. 5i to the 4th is 5. I'm missing... Oh, this is I to the 5th, not I to the 6th. I to the 5th is the same thing as just I again. 1 minus 10, negative 9, plus 5 is negative 4. This becomes negative 4, and 5 minus 10i is negative 5i, plus I is negative 4i. So negative 4 minus 4i. There are actually other ways to get that using other things. We're not actually talking about those right now. All right, part B. 3 minus I to the 6th power. So 6 was 1, 6, 15, 20. Yeah. All right, so this is 3 to the 6th minus 6 times 3 to the 5th times I plus 15 times 3 to the 4th I squared minus 20 times 3 cubed times I cubed plus 15 times 3 squared times I to the 4th minus 6 times 3 times I to the 5th. Whoops, I don't know why that one's in parentheses. Plus I to the 6th. Okay. So 3 to the 6th is, I always forget this. I don't know why I'm forgetting this. 729 minus, oh, we saw these numbers before. 6 times 3 to the 5th. I don't remember it, but whatever. 6 times 3 to the 5th is 1458. Of course. 1458I plus, oh, I squared is -1, right? So I squared is -1. I just need to know 15 times 3 to the 4th. Probably a number we've seen. 1215. I believe so. Minus 1215. Remember, I squared is -1. So minus 1215. I cubed is -I, so this will now become a plus. 3 cubed 27 times. We've seen this. 540. We've seen these numbers before. They think they're trying to trick us, and they're not. I to the 4th is just 1, so I need to know 15 times 9, which is 135. And then I to the 5th is just I, so that's -18I. And then I to the 6th should be I squared again, so that's -1. Okay, so I'm going to use the calculator here. So we'll do 729 minus 1215 plus 135 minus 1. And I'm getting -352. So -352. And then -1458I plus 540I. Sorry, I'm not spending a long time explaining I right now, by the way. Minus 18I. I think it's things you would have done from the previous year. So -352 minus 936I. Really weird numbers there, but I guess that's how that thing would work out. Okay, so let's go to number 92. I'm seriously pressed on time. It's a time factor here. I only have not much room on my thing. I think I'll make it, but I don't know how long these problems are. Abstract reasoning, you're given the function f of x equals x plus da-da-da. When f of x is written in standard form, show the coefficient of x cubed is the sum of a, b, c, and d, and the constant term is the product of a, b, c, and d. The coefficient of x cubed. So x cubed, x plus a, x plus b, x plus c, x plus d. I guess I do have to expand it. Sort of. Well, these are the linear things, but I don't know. Listen, I'll expand it. I know the product must be the constant of all those ones, because that's when x is 0. Or the constant's the product of all those. But show the coefficient of x cubed is the sum of those. I mean, those are different numbers, so I guess I just got to expand it. All right, so I'm going to do the first two. That's x squared plus a plus bx plus ab. And this, okay, so this might be a way to be able to do it. And this is x squared plus c plus dx plus cd. I'm doing this here to keep these treated as a single term. This is ax plus bx, and this is cx plus dx. So now when we expand everything here, this will be, oh boy, this is going to be tough. X to the 4th plus c plus dx cubed plus cdx squared. Now let's do the a plus b things. Plus a plus bx cubed plus a plus b. Oh, shoot. This one I have to do, well, here's where, you know what? I don't care about the rest of them. I care about the x cubes, right? So the x cubes right here, this one, c plus dx cubed plus a plus bx cubed is going to be, listen, I can expand this out. That's ax cubed plus bx cubed. I had them separate, but I might as well expand them now. I thought it was going to help to keep them kind of compacted, but expanding helps. Plus cx cubed plus dx cubed, which now factors out in a plus b plus c plus dx cubed. So I had them together in factorization when they could have been expanded, but I factor out the x cubed after that, and that's what I get as a result. Now, the last one is just all four of these multiplied, a times b times c times d. You know, when I do this, you can see right here, a, b, and c, d are going to multiply there, and you get A, B, C, D. So I'll leave that at that. That makes most sense as far as it goes. Remember, the constant term's also the value when x equals 0. You substitute 0, that's all you'll get. That term's going to exist. All right, number 93, drawing conclusions. Let g of x, there are 4 parts to this. Let g of x equal 12x to the 4th plus 8x plus 9, and h of x equal that guy. What is the degree of the polynomial g of x plus h of x? They're not asking to explain. It's all about the degree. Degree of the polynomial is going to be, degree equals 5. It's still going to be the leading term. Doesn't matter when they combine, as long as nothing cancels. The x to the 5th doesn't cancel. The degree is going to be 5. Part B. What's the degree of the polynomial on this guy? I'm going to kind of change this thing. I'm going to draw an arrow. Degree is 5. Here, the degree is still going to be 5. Again, the x to the 5th does not cancel. The degree is still 5. Part C. What is it for g of x times h of x? This one's a little different. What's going to happen is ultimately the two highest ones will multiply somewhere. X to the 4th times x to the 5th. X to the 4th times x to the 5th equals x to the 9th. So degree is 9 on that guy. So 5, 5, 9. These are quick parts at least. Part D. In general, if g of x and h of x are polynomials such that g of x has degree m and h of x has degree n, and m is greater than n, what are the degrees of g plus h of x, g minus h of x, and g times h of x? So yeah, as they said those, notice how the things never canceled, and they couldn't cancel because they aren't like terms. So if g of x plus h of x, remember g of x has degree m, and that's bigger than m. So g of x plus h of x degree is m. G of x minus h of x degree is still m. The degree won't change just because you subtract something, but when you multiply them, those things will add. G of x times h of x degree is, degree is m plus n, because the exponents multiply if those are the two highest ones. Not the two highest ones. Well, yeah, the two highest ones, and they end up multiplying at some point together at a part. So that'll be it. All right, there's part D. All right, kind of a quick question. Number 94, finding a pattern. In this exercise, you will explore a sequence of square numbers. The first 4 square numbers are represented below. Find the differences between consecutive square numbers. Explain what you notice. Well, we've done a lot of these because it's going to be the same thing for quadratics. So 1, 4, 9, and 16, their differences are 3, 5, and 7. I don't know if they're telling us to notice that they're just odd numbers or that their second differences are constant. Remember the plus 2 thing? So they have constant second differences. That can be a part of what we notice. So I'll say constant second differences, or they might mention something about the odd numbers as they go up. I don't know which one. Part B, show how the polynomial identity n plus 1 quantity squared minus n squared equals 2n plus 1 models the differences between square numbers. So n plus 1 squared minus n squared equals 2n plus 1. Oh, because we increased by 2's there. How does it model it, or how does this work? I don't know if that's which. Oh, prove the polynomial identity is what I was thinking of. So the way that this models this is because this here, n plus 1 squared minus n squared, shows the difference in any two things. Shows differences. Shoot. Okay. Let me separate these a little bit. Give me a second. So the one on the left is basically showing the difference, what you do when you subtract one term from another term. Shows difference between two consecutive squared terms. If you think about it, if n was 3, then this is 4 squared minus 3 squared, right? Or if n was 10, it's 11 squared minus 10 squared. That one shows that difference. 2n plus 1 is showing what that difference actually is. Shows what that difference is. Now, actually is. So show how it models the differences. You can take a look and see that if we did from 1 to 2, this would be, 2 squared minus 1 squared, which is 4 minus 1, which is 3, and 2 times 1 plus 1 is 3. Or if I did 3, let's see what the other ones were. 3 and 4. 4 squared, 16, minus 3 squared is 7. 2 times 3, 6 plus 1 is 7. So it all works out there. Part C, prove the polynomial identity. I have to show that n plus 1 quantity squared minus n squared equals 2n plus 1. I'm going to keep 2n plus 1 the same on that side. Over here, I'm going to expand this to n squared plus 2n plus 1. And you have a minus n squared. And the n squareds cancel when you subtract them, and you're left with 2n plus 1 equals 2n plus 1. So it does seem to work out. And that's just a true thing we know about quadratics and their second differences being constant all the time. Okay, I think we're going to be able to finish on time, which is good. Number 95. I was kind of pressed for time, and I know I've been rushing on some of these, but let's see if we can finish before 4 hours even. Last one, number 95, critical thinking. Recall that a Pythagorean triple is a set of positive integers a, b, and c such that a squared plus b squared equals c squared. The numbers 3, 4, and 5 form a Pythagorean triple because 3 squared plus 4 squared equals 5 squared. You can use the polynomial identity x squared minus y squared x squared minus y squared squared plus 2xy squared equals x squared plus y squared squared to generate other Pythagorean triples. I didn't know that. Prove the polynomial identity is true by showing that the simplified expressions for the left and right sides are the same. All right, let's go and simplify this. X squared minus y squared squared expands to x to the fourth minus 2x squared y squared plus y to the fourth. 2xy quantity squared is positive 4x squared y squared. X squared plus y squared quantity squared is x to the fourth plus 2x squared y squared plus y to the fourth. Now, negative 2x squared y squared plus 4x squared y squared is positive 2x squared y squared, so it shows that these two are the same. Oops, that's a y. Let me fix that. Plus y to the fourth. Okay, all good. That's part A. Part B. Use the identity to generate the Pythagorean triple when x equals 6 and y equals 5. All right, do they want us to do the original one? So, or any of them? Oh, I guess the identity one. So when x is 6, y equals 5, let's check and see that 6 squared minus 5 squared squared plus 2 times 6 times 5 squared equals 6 squared plus 5 squared squared. I never knew that this works. 36 minus 25 squared plus 60 squared. Oh, so these are by the way the numbers that we're working off themselves. So this is 11 squared plus 60 squared. Basically, these are the Pythagorean triples: 11, 60, and 61. Is that what that is? Let's see. I know 11 squared is 1,331. 60 squared is 3,600. Let's check if 61 squared is the number we want it to be. 61 squared, 3,721. What? Let's see. Well, then that didn't work. 36 plus 25 is 61. 61 squared, 3721. 11 squared. Oh, sorry. 11 squared isn't 1331. That's 11 cubed. I'm sorry. That's 121. Okay. Got it. I was thinking too much of Pascal's triangle stuff. So 3721 equals 3721. Okay, that one checks out. I mean, it should, because the formula we just used. Verify your answer in part B satisfies a... Oh, I thought that's what they just did. Oh, So the Pythagorean triple, oh, okay, I kind of screwed up. But the Pythagorean triple is 11, 60, and 61. Now, that's part B. Part C, I guess, is this: verify your answer satisfies a squared plus b squared equals c squared. I just did. Yeah, that was supposed to use those other parts there. I think we're all good to generate the Pythagorean triple. Yeah, I think I was able to do that there. So anyway, that shows that it works out. That's part C. Part B, I ended up kind of doing within part C. I don't know how you do part B without part C, really, to be honest. All right, guys, that ought to do it for this one. This is Mr. Robinson. Thanks so much for watching. That was a long one. My TV shut off at some point as well. Yeah, I hope everything pans out exactly as you needed it. We're going to jump into dividing polynomials next, so take care. Thank you. I will see you in the next one.